Delayed choice quantum eraser. There's something about time that feels unshakable, like a path we can only walk in one direction, with every step locked behind us, untouchable and final. But deep inside the strange territory of quantum physics, there's an experiment that calmly, quietly, tells us that might not be the case at all. It's called the delayed choice quantum eraser, and what it suggests is that reality might be more fluid than we ever imagined, that the future and the past might not be as separate as we think, and that observation itself could be the thread that ties it all together. To even begin understanding this, we need to go back to a much older experiment called the double slit, where particles like photons are fired toward a barrier with two small slits, and behind that is a screen where we see where the particles land. When you don't measure which slit each photon goes through, they form this smooth interference pattern, like waves overlapping each other, as if each photon went through both slits at once and interacted with itself. But when you place a detector to find out which slit it actually passes through, the pattern disappears completely. Instead of behaving like a wave, it acts like a simple particle, choosing one slit or the other, leaving a very different pattern on the screen. That alone is already strange. Just the act of observing changes what the particle does. But the delayed choice quantum eraser goes even further. It asks what happens if we make the choice about whether or not to observe the particle's path only after the particle has already hit the screen. It sounds impossible, even ridiculous, but the experiment has been done more than once, and the results remain the same every time. In this version of the experiment, scientists use pairs of entangled photons. That means their properties are linked, no matter how far apart they travel. One photon goes toward the double slit, through it, and onto the screen where it lands. The other photon, its twin, is sent on a longer path, through mirrors and beam splitters and detectors, to be measured later. The choice to either preserve or erase the which path information is made only after the first photon has already landed on the screen. And yet, the results change depending on what choice is made with the second photon. If the which path information is erased, the interference pattern returns. It's as if the first photon knew it was allowed to behave like a wave. If the information is preserved, the interference disappears. The first photon behaves like a particle. But here's the thing. The choice to preserve or erase happens after the first photon has already finished its journey. This is where the mind quietly starts to dissolve around the edges. Because it doesn't make sense in any way that matches our everyday understanding of time. The effect comes after the event, and still somehow decides how that event unfolded. It's not about sending messages back in time, and it doesn't mean we can change the past in any ordinary sense. But it does mean that reality, at this deep quantum level, might be waiting for context before it settles into place. That's the haunting beauty of it. The universe isn't acting like a fixed machine with gears and rules that grind forward, unaffected by our attention. It's behaving more like a story that adapts itself depending on how we choose to read it, or a painting that shifts depending on where we stand. It doesn't change because we touched it. It changes because we sought to know it, and the moment we choose to look or not look. The fabric of what happened adjusts to stay consistent with our knowledge. There's no single explanation that fully resolves this. Some interpretations of quantum mechanics suggest the particle never really takes a path until it's observed. Others say all possibilities exist, and our observation simply filters one reality out of many. But whichever interpretation you choose, the result is the same. Our choices matter, not just in shaping the future, but possibly in shaping how the past appears to us. And what does that mean for us, in this quiet moment, lying in the dark? Letting these thoughts float through us, it means that maybe reality isn't finished. Maybe it isn't solid until we decide to touch it. Maybe the past isn't a closed door, but a window that still responds to how we see it. It's not that the universe is trying to trick us, or that physics has gone wrong. It's more like we've reached a place where the rules we built no longer apply, and we're seeing the raw possibilities of existence before they get painted over by logic and memory. That's what the delayed choice quantum eraser shows us. Not a universe that disobeys its own rules, but a universe whose rules are deeper than we thought, more subtle, more patient, and maybe even more aware. So if you find yourself drifting off while thinking about this, that's okay. Let it happen. Let your mind let go of the hard edges and straight lines. Because in this quantum world, things don't have to happen in order. Particles don't have to choose just one path. And sometimes, the answer only arrives after the question has already been asked. False vacuum decay. There's a comforting lie we all live with, quietly humming underneath everything we do. It's the idea that the universe, no matter how wild or unpredictable, is at least stable, that the ground beneath our feet and the laws behind the stars are locked in place. But in the cold silence of theoretical physics, there's this quiet little monster lurking in the corner. It's called false vacuum decay, and it suggests that everything we think is permanent might just be running on borrowed time. To understand this, you have to let go of the idea that empty space is really empty. Because even in a perfect vacuum, there's something there, a baseline of energy. This is called the vacuum state. Think of it as the lowest possible energy level that space itself can settle into. But just like a ball resting in a shallow valley, what feels like the bottom might not actually be the true bottom. There could be a deeper valley, a more stable state of existence, hidden further below. And if that's the case, then we are living in a false vacuum, a fake floor that only feels solid because we haven't fallen through it yet. Now imagine that at some point, somewhere in this universe, that fake stability gives way. The ball suddenly finds the true valley and drops. When that happens, the laws of physics as we know them don't just shift, they collapse. Everything we understand about matter, particles, gravity, time, all of it gets rewritten in an instant. The universe doesn't explode. It transforms. The very structure of reality dissolves and rebuilds itself with a different set of rules. And here's the part that really turns your stomach. If false vacuum decay happens, it spreads outward at the speed of light. A bubble of true vacuum forms, and like a silent shockwave, it expands across the universe, erasing and rewriting everything in its path. But because it moves at light speed, you don't see it coming. There's no warning, no sound. One moment you're alive, thinking, breathing, and the next, you and your entire region of space are just gone, converted into something completely alien, and you wouldn't even have time to know it happened. That's the horrifying beauty of it. It makes you. There's no debris, no aftermath, no escape plan. It's just pure, absolute change, and we would never see it arrive. So how real is this threat? Is it just a clever piece of theoretical drama, or is it something the universe is actually doing right now? Well, according to some calculations, and this is where things get unsettling, false vacuum decay is not only possible, it might already be inevitable. The Higgs field, the invisible energy field that gives particles their mass, plays a big role here. When scientists discovered the Higgs boson back in 2012, they also measured its mass. And that number was a little too perfect, a little too balanced. It placed us right on the edge between stability and decay, not safely above the true vacuum, not far below it, but teetering on the edge. Almost like a cosmic accident waiting to happen. It gets worse. If the current state of the universe is a false vacuum, then it's not a question of if it will decay. It's a question of when. The odds might be low. The timescale might be incomprehensibly long. But in the grand scope of eternity, even the rarest event becomes a certainty. Somewhere out there, that bubble could have already formed. It could be expanding right now, racing through galaxies at the speed of light. And we'd never know. We'd never feel it. We would just be gone. But here's where the weirdness deepens. Some physicists argue that false vacuum decay could have already happened countless times in the universe's past, just not in our region. In this view, entire regions of space are constantly peeling away into new versions of reality, each with different laws, different particles, maybe even different kinds of time. From our perspective, it's invisible. But from the universe's perspective, it's just business as usual. Constant reinvention, constant mutation of the fabric of what is real, and then you wonder, what happens inside that new vacuum? What does existence look like there if consciousness is even possible? Would anything in that bubble remember what came before? Would it know it was part of something that once felt stable? It's this slow, burning, existential anxiety that makes false vacuum decay so terrifying. Not because it's likely to happen in our lifetime, not because we can stop it, but because it quietly reminds us that stability is not guaranteed, that what we call reality might just be a temporary phase, a local version of physics that feels universal only because we have not yet been rewritten. So you sit with this idea, that space itself might be fake, that every moment, every breath, every choice could be balanced on a thin crust floating above a deeper, more final truth, and that someday, maybe today, maybe in a billion years, that truth decides to break through. And when it does, nothing screams, nothing burns. The universe doesn't care. It just shrugs, tears off the mask, and becomes something else entirely. Wigner's friend paradox. There's this strange moment we all experience when we catch someone deep in thought and wonder what they're thinking. Like, what exactly is happening inside their head that we can't see? But in quantum physics, that innocent question spirals into something much deeper, much stranger. The Wigner's friend paradox takes that private internal world and shatters the idea that there even is a single objective reality. Not because of imagination or psychology, but because physics itself might allow two different versions of the same event to be real at the same time. Here's how it goes. Imagine there's a scientist locked in a lab. We'll call them the friend. Inside the lab, they run a simple quantum experiment. A particle exists in a superposition, let's say spin up and spin down. It's both states at once until someone measures it. So the friend opens the box, observes the particle, and sees that it's spin up. In their world, the wave function has collapsed. The outcome is real, they've seen it. Case closed. But outside the lab there's another person, Wigner, and from his point of view, the entire lab, including the friend, the equipment, and even the result, is still in a superposition. Until Wigner makes a measurement, the whole system is floating in a cloud of possibilities. So in Wigner's universe, the friend has both seen spin up and spin down. The lab is not locked into one truth, it's still both, and that's where things get uncomfortable. Because now, we have two observers who are both following the rules of quantum mechanics, but they disagree about what's real. Not because one is wrong, but because they exist in different frames of truth, and it doesn't stop there. The friend will swear they saw a definite result. Wigner will swear the lab is still in limbo. So who's right? Is the friend hallucinating reality before Wigner opens the door? Or is Wigner missing something that already happened? And if both are correct within their own slice of reality, then reality itself might not be one coherent whole. It might be fractured, dependent, subjective in a way we're not used to accepting. It sounds like philosophy, but it's physics, pure quantum mechanics. The math allows both interpretations. The friend experiences a definite event. Wigner sees a quantum soup. And neither can be fully dismissed without breaking the rules. So suddenly, we're faced with a deeper, more uncomfortable possibility, that objective truth, the thing we rely on to agree on what happened and what didn't, might not actually exist in the way we think it does. And now you start to wonder what this means for your own consciousness. Because if two people can disagree on a measurement that supposedly already happened, then what is observation really doing? Is it locking reality into place? Or is it just carving out one version of it for one observer at a time? Some interpretations try to escape this weirdness. The many worlds view says every possibility becomes real in a separate branch of the universe. So both the friend and Wigner are correct. They're just living in different worlds. But that answer, while neat on paper, opens a different can of worms. It means every moment, every choice, every possible measurement splits reality into more and more versions. You're not just living in the universe. You're fracturing it with every blink. Other interpretations try to protect the idea of a single objective reality by saying consciousness itself causes collapse. That when the friend observes the result, the wave function collapses universally, and Wigner is simply unaware of the outcome until he checks. But that raises its own questions. Like, what is consciousness actually doing here? Is your awareness somehow the force that shapes the universe? And if so, how far does that go? Does every conscious moment rewrite the structure of everything else? You sit with these thoughts and they don't really settle. Because no matter how you cut it, the paradox remains. Wigner's friend saw something. Wigner saw something else. And the rules say they're both right. The contradiction isn't a bug. It's baked into the system. So now the question stretches wider. What if this isn't just about labs and particles? What if reality itself is made up of overlapping narratives? What if truth is not one single thread we're all walking together, but a web of threads that only look the same until we start comparing notes? Your version, my version. Each one clean and complete, but maybe not fully compatible. And that's when the quiet terror starts to creep in. Because if observation is relative, then so is memory, so is history, so is time. If what's real depends on who is looking, and when, and how, then the fabric of the universe might be far softer than we thought. It might not be a grid. It might be a fog, and your awareness is just a flashlight cutting one narrow beam through it. That's what Wigner's friend forces us to face, not just the unreliability of perception, but the possibility that reality itself is participatory, dependent on minds, on views, on observers who will never fully agree because the universe doesn't offer a single answer. It offers probabilities, possibilities, branches, versions. So you sit with that, in the dark, thinking not just about what's real, but who gets to decide. And whether the truth is ever truly out there, or whether it's just echoing quietly in your own mind, waiting to collapse into something you can call real. Holographic noise. Sometimes it feels like space is just there, an empty container. A quiet stage where reality plays out. We move through it, measure it, even launch telescopes deep into it, assuming it's smooth and silent and infinitely detailed. But what if space itself is not what we think it is? What if instead of being perfectly real and continuous, it's actually fuzzy, like a blurry digital screen when you zoom in too far? That's the strange idea behind something called holographic noise. And if it's real, it might mean the entire universe is a kind of projection. To even begin unpacking this, you have to imagine something wildly unintuitive. The thought that space is not continuous, that it doesn't stretch in an infinite spectrum of smooth coordinates, but is instead made of bits. Not bits like atoms or particles, but bits of information, like pixels, like data. The idea comes from a concept in theoretical physics called the holographic principle. It suggests that all the information contained inside a volume of space might actually be encoded on its surface. Kind of like how a hologram on a credit card looks 3D, but is actually 2D. Our three-dimensional world could be a projection of information stored on a distant two-dimensional boundary. Now that sounds poetic and abstract, and maybe even beautiful. But holographic noise is the part that gets under your skin. Because if the universe is encoded like a hologram, that encoding might not be perfect. It might have jitter, a fundamental grayness, a natural fuzz at the edges of reality, like static on an old radio, except this static is woven into space itself. And here's where it starts to feel real. If space is made of finite information, that means it can only resolve details down to a certain limit. Anything smaller than that becomes uncertain, indistinct, blurred. So just like a camera has a resolution limit, the universe might have one too. It's not because our tools aren't sharp enough. It's because reality itself might not be built to give us perfect clarity. There's a ceiling on how crisp things can get. That ceiling is where the noise lives. And it's not the kind of noise we hear. It's positional noise. Jitter in the fabric of space. Think of 2 points floating in the void. You might think you can measure the distance between them with absolute precision. But if holographic noise is real, there's a tiny fluctuation. The positions wobble ever so slightly, not from outside forces, but from something deep inside the way space is structured. Some physicists believe we might actually be able to detect this. That's where things get really wild. There have been experiments like the holometer, a pair of interferometers designed to pick up these tiny spatial jitters. 2 high-precision laser systems set up to detect whether the fabric of space itself is vibrating in a strange way that would suggest it is holographic. The results have been debated, unclear, inconclusive, but even the idea that we could look for this kind of noise is disturbing. Because it's like trying to find the pixel grid behind the universe's display. It's trying to listen for the hum of the projector that's casting our world into form. And you start to wonder what it would mean if that hum is real. If this space we move through, this room, this planet, this galaxy, is a kind of shadow, a shimmering 3D echo of information written elsewhere. It breaks everything we assume about locality, about reality. Because in a holographic world, distance might not be what we think. The space between here and the moon, or here and the edge of the universe, could just be a visual effect, a byproduct of how the information is decoded. And this is where the discomfort settles in. Because if space is not truly continuous, if the sharp edges we trust are really soft, then every step we take, every boundary we observe is a kind of illusion, not fake, not meaningless, but simulated, a rendering. And holographic noise is the background flicker that proves we're watching a film and not standing on a stage. What makes it even more unnerving is that this wouldn't just be a metaphor. It's not like saying the universe is like a dream or a simulation as a poetic thought. It would be literal, encoded, projected, real in the way a video game is real to the characters inside it. The physics still work. The world still moves. But the depth and smoothness we trust might be built on something far thinner than we think. So you lie back and look at the ceiling, or the sky, or the dark, and you ask yourself, how much of this is actually there? How much is just a high-resolution experience that starts to stutter when you zoom in too far? And if it's all noise underneath, who or what is decoding it? Who is holding the lens? And why does it feel so real if it's just light bouncing off a boundary somewhere far beyond what we can reach? That's the weight of holographic noise. It's not loud. It doesn't break anything. But it whispers that space might not be infinite. It might be a painting, a film, a ripple on a surface we'll never see. And that the blur is not the failure of our tools. It is the nature of the canvas itself. Quantum Cheshire Cat. There's something deeply unsettling about seeing a smile without a face. That's what made the Cheshire Cat so creepy in Alice in Wonderland. It fades away slowly until all that's left is the grin, just hovering there, disconnected from everything else. Now, that kind of thing should only happen in dreams or fiction, not in real life, and definitely not in physics. Except it does. In the quantum world, particles can do something just as eerie. Something called the quantum Cheshire Cat, where a particle and one of its properties, like its spin or polarization, can become separated, not metaphorically, literally, like the grin and the cat going different directions. Here's the weird setup. You take a neutron, a tiny subatomic particle. It has mass, it has position, and it also has spin, which is kind of like its orientation, like a little arrow pointing a certain way. Now, we pass this neutron through an interferometer, basically a system that splits its path, sends the particle down 2 possible routes, and then brings them back together. This is standard quantum mechanics stuff. A particle goes into superposition. Both paths are possible. Nothing unusual there. But then comes the twist. We start measuring. Gently. Not in a way that collapses the wave function right away, but in a weak, almost whispering kind of observation. The kind that nudges the system just enough to collect information without forcing it to choose a path too early. And when scientists did this, they found something that should be impossible. The neutron went one way, but its spin went the other. Like the cat walking left while its grin floats off to the right. So now we're faced with a question that cuts straight into what we think particles even are. If the neutron is here, but its spin is over there, then what is the neutron? Is it a collection of properties bundled together? Or can those properties be peeled off, like layers, and sent wandering on their own? The result is not just a trick of measurement, it's baked into the math. The equations say this separation is allowed. Not only allowed, expected under the right conditions. A property of the particle can be found in a place where the particle itself is not. That shakes something fundamental loose. Because we tend to think of an object as a unified thing. A pen is not in one place while its blueness is in another. Your body is not here while your left-handedness floats 5 feet to the side. But in quantum mechanics, that unity collapses. Identity fragments. A particle is not a marble with labels. It's a blurry, shifting smear of possibilities, and sometimes those possibilities can split like oil in water. And here's where it gets even stranger. This isn't just a random fluke. It's repeatable. Predictable. You can build an experiment where every single time the particle and its grin part ways. This has been done with photons too, splitting them from their polarization, their spin, their momentum. All those traits we think are tied to the object. Turns out, they can wander. So now you're forced to ask, what makes something what it is? Is the particle still a particle if it loses a property? Is the grin still a grin if there's no cat? And if identity is this fragile, this fluid, then maybe the idea of a solid, indivisible object is just something we invented to feel safe in a chaotic universe. And it gets worse when you zoom out. Because this isn't just a physics problem. It's a consciousness problem. If particles can be split from their traits, then what about us? Are we as bundled up as we think? Or are we also smeared out? Traits floating one way, thoughts another. We don't notice because we live in the classical world. Everything appears clean and tied together. But that's just a surface layer. Underneath, everything is soup, quantum soup. And in that soup, even identity is optional. There's a philosophical ache here. Because it forces us to confront the idea that objects might not be real in the way we assume. A particle is not a tiny thing with properties. It's more like a field of maybe, a cloud of probabilities, and sometimes those probabilities go on vacation without each other. And if that's true for particles, the most basic ingredients of reality, then what is anything built from them? Are we stable structures or just temporary alliances of traits? Is your mind just a coincidence of functions that haven't floated apart yet? You sit with this thought, and it doesn't settle. It expands. Like smoke, you start to wonder how many things in your world only feel solid because you're not looking too closely. How many smiles are hovering where no face exists? How many traits you think are yours are actually somewhere else? That's the power of the quantum Cheshire Cat. It's not just a clever name. It's a warning that underneath the stage lights of classical physics, there's a wild and deeply strange play being acted out in total darkness, where particles lose their properties, and properties lose their homes, and reality doesn't care if that makes sense to us or not. So the next time you think you understand what something is, where it is, how it's behaving, just remember the cat. The one that vanished but left the grin behind. Because that might be exactly what reality is doing to us right now. And we're just smiling along with it. Quantum Darwinism. There's this unspoken assumption we all carry around. That the world exists whether we're looking at it or not. That the chair is still there when we leave the room. that the moon doesn't blink out of existence when nobody's watching. We don't question it because it feels obvious. Of course, reality is real. But quantum physics has always had this glitch, a tiny crack in that certainty, because deep down, the rules say nothing becomes definite until it's observed. Until then, it's not here or there. It's not one thing or another. It just floats, unresolved. So if everything depends on being measured, then how does the world ever become stable enough for us to live in it? That's where quantum Darwinism comes in. It's one of the wildest ideas in modern physics, but it also might be the reason you're able to sit in a room and trust that the floor won't disappear. It tries to answer this huge, uncomfortable question. How does the fuzzy, blurry, indeterminate quantum world turn into the crisp, solid reality we experience every day? The idea starts with something you already know from regular Darwinism: natural selection. Traits that survive are the ones that spread. The same thing, strangely enough, happens in the quantum world. When a particle exists in a superposition, meaning multiple states at once, it can interact with its environment in countless ways, but only certain outcomes end up getting copied into the environment over and over. Only some states leave records. Only some make themselves known, and those are the ones we end up seeing. So what does that mean? It means that reality doesn't become real all at once. It's not like the universe flips a switch and decides something happened. Instead, what happens is that certain quantum states get amplified, repeated, echoed. They imprint themselves on the world around them, on photons, air molecules, particles. They leave footprints, and those footprints spread. Here's the twist. We never directly observe the quantum system itself. We observe the copies, the imprints. The environment around it is telling us the story. So what we call objective reality is really just the version of events that left the most footprints behind. Imagine a glass shattering on the floor. The sound bounces off the walls. The shards reflect light. Heat transfers into the air. The event gets broadcast in a million different directions. That's decoherence, the process of a quantum system bleeding into its surroundings. But quantum Darwinism adds a second layer. It says the only reason you know the glass shattered is because that particular version of the event got copied more than the others. The universe could have chosen other paths, but those didn't leave strong enough trails. So the world you see, the objects, the outcomes, the history, is basically the survivor of a quantum popularity contest. The interpretations that spread win, the rest fade into silence. And this is where it gets unsettling, because now you're faced with the idea that what you think of as real is just the version that managed to go viral. Other possibilities were there. Other versions of the event could have crystallized, but they didn't make enough noise, so you never knew they existed. Think about that for a second. Reality isn't picked by some cosmic judge. It's selected by redundancy. The more an outcome echoes into the environment, the more observers can agree on it. And once everyone's measuring the same thing, it starts to feel real, not because it was destined, but because it was copied. That might not sound dramatic at first, but it quietly shatters everything we thought we knew about objectivity. The moon is there when nobody's looking, not because it was always solid, but because its presence is constantly reinforced by trillions of environmental interactions. It's being measured all the time by everything around it. It's being copied so thoroughly that it becomes stable, becomes classical, becomes real. And the freakiest part is this: it doesn't require a conscious observer. You don't need a human to collapse the wave function. The environment is doing it automatically. Every leaf, every photon, every molecule is part of this giant measurement network. They're recording events without knowing it. And from that sea of imprints, reality emerges. It's not a universe of things. It's a universe of information, of signals bouncing off surfaces, echoing through time, competing to be noticed. And the ones that win are the ones we call truth. So you might be walking through a world that feels solid and objective and fully baked, but in reality, You're living inside the winning version of countless quantum outcomes. Your life, your memories, your sense of what just happened. All of it might be the result of quantum patterns that just happened to leave the strongest trail. And now you can't help but wonder how many things almost happened. How many versions of reality are out there, never copied, never shared, never known. A universe full of events that blinked in and out of quantum possibility without ever getting their big break. That's the genius and the terror of quantum Darwinism. It takes something as small as a particle and shows you how it scales up into the stage we live on. But it also whispers that reality didn't choose you. It just replicated something enough times that you ended up believing it was real. EPR Conjecture. You ever have that moment where two completely different things in your life suddenly connect, and you can't unsee it? Like a weird déjà vu, but it rewrites your entire understanding of how everything fits together. That's kind of what happened to physics when ER=EPR dropped onto the table. It's not a theory. It's a jaw-dropping suggestion that two of the most mysterious ideas in the universe might actually be the same thing. Black holes and quantum entanglement, gravity and information, space and connection, all tied together by a bridge we didn't even know existed. Let's take this one slow. Back in the 1930s, Einstein and Rosen came up with a solution to his equations that described what we now call a wormhole. A tunnel in space, time that connects two distant regions of the universe. They called it the Einstein-Rosen bridge. That's the ER part. The idea is simple to picture but hard to swallow. You have two black holes, and there's a tunnel linking them. Not a shortcut you can travel through, but a weird connection baked into the geometry of space, time. Now skip forward a few decades. In the world of quantum mechanics, there's something called entanglement. Two particles become linked in such a way that measuring one instantly affects the other, even if they're light years apart. This is the EPR part, named after Einstein, Podolsky, and Rosen again. Einstein famously hated it. He called it spooky action at a distance. But experiments have shown over and over, it's real. So here's the shock. Two ideas that seem completely unrelated. One is about black holes in space, time warping in general relativity. The other is about subatomic particles sharing information in quantum mechanics. Totally different scales. Totally different rules, and yet, in 2013, physicists Juan Maldacena and Leonard Susskind proposed something almost unthinkable. That maybe ER and EPR are not two separate mysteries. Maybe they're two ways of looking at the same thing. The claim is that an Einstein-Rosen bridge, a wormhole, is physically equivalent to entanglement. That whenever two particles are entangled, they are connected by a microscopic wormhole. Not the kind you can fly a spaceship through, but a thread in the fabric of reality itself. Let that land for a second. Because if that's true, then entanglement is not just information being shared, it's space itself being stitched together. The invisible link between particles is actually a tiny bridge in space-time. So now you start asking questions. What is space, really? Is it something that exists independently, or is it made from relationships? From entanglement? Because if enough of these quantum connections exist between particles, maybe that's what builds the shape of space itself. Maybe gravity is just the large-scale effect of entanglement weaving the universe together. And suddenly, this changes the game. Because general relativity has always been great at explaining the big stuff. Stars, planets, galaxies. And quantum mechanics rules the tiny, weird world of particles. But for decades, they refused to play nice with each other. Gravity and quantum physics just wouldn't merge. ER=EPR might be the first real thread that connects them. Now it starts to feel like a movie plot. Black holes evaporate because they lose entangled particles. Wormholes emerge because entanglement pulls space into shape. You realize this might be the real architecture behind reality, not objects floating in space, but a network of entangled links that actually is space. It's so counterintuitive. It breaks your mental furniture. Because now, distance becomes meaningless. If two particles are entangled, they are not far apart in any real sense. They're connected by a hidden tunnel. And space, as we experience it, might just be the illusion that forms when enough of those tunnels exist. But it gets even darker when you go deeper into black holes. One of the biggest problems in physics has been the black hole information paradox. If something falls into a black hole and the black hole evaporates, where does the information go? Quantum mechanics says information can't be destroyed, but black holes seem to eat it. If ER equals EPR is correct, then maybe that information doesn't vanish. Maybe it leaks out through the entangled particles connected by wormholes. Maybe the entire interior of the black hole is encoded on the outside, stored in the entanglement with the rest of the universe. Now think about that. If the interior of a black hole is just a different view of its entangled connections, then even death, even the collapse of matter beyond an event horizon, might be reversible, not in a science fiction way, but in a cold, mathematical, uncomfortably real way. That's what this idea does. It doesn't just connect two theories. It bends your idea of what space is, what connection is, what reality is made of. It suggests that the entire universe is a web of quantum relationships, and that geometry, the shape of everything, is just the echo of those relationships spreading out. So next time you look up at the night sky and think about how far everything is, try flipping it. Try thinking not in terms of distance, but in terms of connection. The stars are not far. They're just less entangled. The people you miss are not lost. They're just no longer linked the same way. Space might not separate us. It might only measure how many wormholes we forgot were there. Twistor Theory. Everyone's walking around thinking the universe is made of space and time. Like that's just the canvas, the background, the thing reality happens on. But what if that entire picture is wrong? What if space and time are not the foundation? What if they're just side effects of something else? A kind of illusion, a projection of a deeper structure that we never see directly. That's what Twistor Theory is. And it's not science fiction. It's one of the strangest and most beautiful attempts to rewrite how we understand literally everything. You live your entire life on a grid. Not one you see, but one you assume. Everything has a location. Everything has a moment. You are here now. That's how physics works. That's how your brain works. And so far, space, time has done a pretty good job. Einstein used it to explain gravity. Quantum mechanics used it to predict particles. But they never played well together. Gravity and quantum physics just won't merge. It's like trying to glue two puzzle pieces together that technically fit but never lock. Something's off. Something underneath the math is broken. So here comes Twistor Theory. And it does something wild. It says maybe the problem is space, time itself. Maybe we've been building the house on the wrong foundation. Instead of describing reality as stuff happening in space at a time, what if we describe it entirely in terms of light? Not where things are, but how light moves. Not when things happen, but how light flows between them. It flips the whole setup inside out. In this framework, the basic unit is not a point in space and time. It's something called a twistor. And again, don't think of it as a particle or a thing. Think of it as a kind of direction, a beam, a trajectory that light could take. A twistor doesn't care about when or where. It cares about the angle, the geometry, the relationship. And when you start describing the universe using twistors instead of coordinates, weird stuff starts to make sense. Particles aren't dots anymore. They're patterns. Fields aren't just forces spread across space. They're connections between twistors. Interactions between particles become clean lines instead of mathematical nightmares. And the equations that describe them, which in normal physics can take up dozens of pages, suddenly collapse into something elegant, something you can almost see. That elegance is a clue, because nature loves simplicity underneath the chaos, and Twistor Theory makes some of the ugliest problems in physics strangely beautiful. Scattering amplitudes, which tell us how particles bounce off each other. become almost effortless to calculate in Twistor space. Like the math was always trying to get us to look from this angle. But it gets deeper. Because once you start thinking in twistors, something terrifying happens. Time starts to fall apart, not in a dramatic way, but in a quiet, permanent way. Because twistors don't care about time the way you do. They don't track before or after, they just describe connections, alignments. If enough twistors line up a certain way, an event appears. If they don't, it doesn't. Time becomes a consequence, not a cause, and now space starts to go too. Because again, twistors don't measure distance, they measure structure. And when you add enough of them together, space seems to emerge. But it's not baked in, it's built. So what you think is the fabric of reality, the 3 dimensions around you plus time, might actually be an illusion created by the way twistors combine. It's like you've been staring at shadows your whole life, and suddenly someone shows you the object casting them. That's what Twistor Theory is pointing at. It doesn't just unify gravity and quantum mechanics, it removes the battlefield completely. Instead of trying to mash them together in space, time, it rewrites the script in a different language. One where the contradictions never even show up, where the math is already smooth, where particles and fields and geometry all flow from the same source. Now, this isn't just a neat idea that sounds cool in theory. It has teeth. Researchers have used Twistor-based models to calculate real particle interactions that match experimental results. In some cases, they do it faster and cleaner than the standard quantum field theory approach. It's not finished. It's not complete. But it's breathing. It's moving. And every time it solves something the old way couldn't, you feel that pressure, that this might be it. Because if Twistor Theory is right, you are not living in space and time. You are living in something built on light paths, on abstract relationships, on a geometry that lives behind what your senses can touch. You are not where you think you are. You are not when you think you are. You are standing in a pattern so complex, so subtle, that it takes an entirely different form of math just to describe the shadow it casts. And if the universe is casting shadows, that means there's something else behind the curtain. Something that isn't space. Something that isn't time. Something that's been running the show while we kept staring at the stage. Transactional interpretation. Imagine you throw a ball across a field. You expect it to move forward, right from your hand to wherever it lands. Now imagine halfway through the throw, the ball somehow starts moving backward, from the future back to your hand, and still completes the throw like nothing happened. That would be insane. That would break every rule of cause and effect we live by. But in the world of quantum mechanics, that kind of thing might actually be happening, all the time, invisibly, quietly, at the heart of everything. Welcome to the transactional interpretation. This thing is like a glitch in the way we understand time itself, because it suggests that events in the quantum world are not just triggered by the past. They're also influenced by the future. That particles don't just move forward through time, but also send out signals backward, like they're negotiating across time to decide what's real. And when that negotiation succeeds, boom, an actual event happens. That's what we see. That's what we call reality. It's not a metaphor. It's the literal mechanism behind how particles behave. Every time a photon is emitted, it sends out 2 waves, one forward in time, one backward. The emitter sends an offer. The absorber responds with a confirmation, but from the future. The transaction locks in. And that handshake across time is what makes something happen. Let that hit you. The future responds to the past, and both come together to make the present. This isn't some wild fantasy. It's a real interpretation of quantum mechanics, proposed by physicist John Cramer back in the 80s, and it's still being explored and debated today. And the reason people can't look away from it is because it solves one of the deepest mysteries in physics, why quantum particles behave like they do only when observed. In standard quantum mechanics, a particle exists in a weird probability cloud. It's not in a definite place or state until it's measured. But why should a measurement cause reality to lock in? What's so special about observation? Why should looking at something change it? Transactional interpretation says, maybe it's not the observation. Maybe it's the transaction itself. The handshake between emitter and absorber. That's what makes the wave function collapse. So when you detect a particle, you're not just seeing the result of a random process, you're seeing the outcome of a two-way deal across time. But here's the shocker, that backward in time wave. It's not some weird side effect. It's necessary. Without it, the whole process doesn't complete. The universe requires both directions, past to future and future to past, to finalize a single quantum event. In other words, what happens now is shaped by both what already happened and what will happen. That should scramble your entire understanding of causality. We like to think time moves one way. Clock ticks. Things age, cause leads to effect. But the math of quantum mechanics doesn't care about that. The equations are time symmetric. They work the same forward or backward. It's only our experience, and maybe thermodynamics, that gives us the illusion of time flowing in one direction. Transactional interpretation takes that symmetry seriously. It doesn't force time to move forward. It allows quantum events to breathe in both directions. It says what looks like randomness might actually be a hidden conversation between what is and what could be. Now, this raises questions that get deeply uncomfortable. If the future can influence the present, then is the future already real? Is it fixed? Can we change it? Or are we just passengers on a timeline that's already been negotiated into place by particles playing a cosmic back, and forth we'll never hear? And if you go even further, you start wondering, what counts as a measurement? If a particle's path gets finalized only when a transaction occurs, then what triggers that? Is it the moment you look? Is it the moment your retina fires? Or is the whole universe constantly absorbing and emitting, constantly finalizing itself in these invisible trades across time? Transactional interpretation doesn't claim to explain everything. It's not a complete theory. But what makes it so haunting is that it doesn't break the math. It works. It predicts the same results as standard quantum mechanics. It just offers a different way to understand what those results mean. One that feels less like a random coin toss and more like a hidden agreement being signed between the future and the past. And the reason that matters. The reason this interpretation might actually be the key to something bigger is because it opens the door to a universe where time is not what we think it is, where cause and effect are more like collaborators than a one-way street, where information can travel both ways, and the present is the result of a negotiation, not a push. That has implications way beyond physics. It challenges free will. It messes with destiny. It makes you wonder if your choices are truly made in the moment, or if they've already been finalized by transactions you can't see. But maybe the most disturbing idea is this. If everything around you, every particle, every interaction, is the result of these time-spanning deals, then maybe the future isn't waiting for you. Maybe it's already shaking hands with the past, right now, silently, unseen. And what you call now is just the moment that deal gets signed. The Firewall Paradox. People think of black holes like bottomless pits, like some cosmic drain you get pulled into if you're unlucky enough to get too close. What most people don't realize is that there's a boundary around every black hole called the event horizon, and for the longest time, physics told us that if you fell past that edge, you wouldn't even feel it. There's no bump, no flash, no sudden burn. It's just space, and then it's not. You'd float across like nothing happened. It sounds strange, but that's what general relativity says. According to Einstein's equations, the event horizon isn't some violent place. It's smooth. You wouldn't even know you crossed it. But that idea has been completely ripped apart by a paradox so intense it's forced physicists to question the foundation of everything we thought we knew about space, time, and reality. It's called the Firewall Paradox, and it turns that quiet event horizon into a wall of raw, high-energy destruction that would instantly vaporize anything that touched it. This isn't a tweak in theory. This is one of those holy shit moments where two laws of physics crash into each other and start screaming opposite answers. It all starts with information. Not digital data or words on a page, but quantum information. The fundamental properties of every particle that makes up everything. And there's a rule in quantum mechanics that says this information can never be truly lost. You can burn a thing, smash it, scatter it across the galaxy, and still the system will contain the pieces of what it once was. That's not a theory. That's law. But black holes seem to break that law. You throw something in, and it's gone, like really gone. Not just the object, but the information that described it. According to general relativity, that data gets lost forever. But if that's true, then quantum mechanics breaks. So something has to give. Stephen Hawking tried to patch it by saying that black holes actually do leak radiation over time, slowly bleeding out energy in the form of what we now call Hawking radiation. It's random and faint, but the idea is that this radiation somehow contains the information the black holes swallow, that eventually all that data gets released and the laws of quantum mechanics are safe. For a while, that answer worked. It was clever. Until someone took a closer look at what it would actually require. To pull that information out, the Hawking radiation would have to be entangled with everything that ever fell into the black hole, but also entangled with itself in a very specific way to preserve the internal logic of quantum theory. And here's the catch. A single quantum particle can't be fully entangled with two different systems at once. That's a hard rule. You can't cheat it. If the radiation is entangled with the stuff inside the black hole, then it can't also be entangled with other radiation particles, escaping outside. So now we've got a conflict. Either entanglement breaks or the information doesn't come out. If entanglement breaks, energy gets released. Not a little, a lot. Enough to create a massive wall of high-energy particles right at the event horizon. A firewall. A zone so hot and so violent that anything falling in gets annihilated on contact. Instantly. That calm, invisible edge becomes a death field. No floating gently through. No peaceful crossing. Just immediate, irreversible destruction. This is where the entire thing collapses into chaos. Because if that firewall exists, then Einstein's theory of general relativity is wrong. It says nothing special happens at the horizon. But if the firewall is real, then the most successful gravitational theory in history breaks down at the very place it's supposed to shine. On the other hand, if there's no firewall and general relativity is right, then we lose quantum unitarity and quantum mechanics falls apart. Either way, one of our deepest understandings of the universe gets shredded. And this isn't just a math issue. This is a philosophical crisis. If information can be lost, then every rule that depends on time running forward and memory existing at all starts to unravel. But if the universe defends that information with a literal wall of fire, then space itself is more violent and unpredictable than we ever imagined. Some physicists try to avoid the question entirely. Maybe black holes are holograms. Maybe space and time are emergent illusions. Maybe there's a deeper theory hiding underneath both relativity and quantum mechanics that fixes the contradiction. Others go all in and say the firewall is real, and that black holes are not what we think. They're not holes. They're information furnaces that incinerate anything trying to break the rules. That edge is not a boundary. It's a punishment. The scariest part is that we may never be able to find out. We can't fly into a black hole and report back. We can't send a camera or a sensor to touch the event horizon and beam data home. Everything we know about it comes from equations, and those equations are at war. So we're left staring at the edge of these monsters, knowing something is wrong, knowing something massive is being hidden behind that dark horizon, and wondering if the universe really does protect its secrets by building walls of fire around them. Because if the firewall is real, then black holes don't just destroy matter. They enforce the truth, and they burn anything that tries to forget it. Axions, you know what's weird about the universe? It moves like it's full of stuff we can't see. Galaxies spin too fast. Stars stay glued together when, by all logic, they should be flinging apart. Massive structures hold shape in ways that make zero sense based on the matter we know exists. That's where dark matter comes in. Some invisible substance, completely undetectable by light, somehow makes up the majority of all mass in the universe. And the truth is, we still don't know what it is. But there's one candidate so strange, so ghost-like, that it might not just explain dark matter, it might fix a totally different problem that's been haunting particle physics for decades. That candidate is the axion. On paper, axions are ridiculously tiny, lighter than electrons, possibly 1 trillion times less massive, and yet they could be absolutely everywhere. Not as a few exotic particles hiding in corners of space, but as a vast cosmic field, a sea of invisible particles streaming through galaxies, passing through planets, flowing through our bodies right now, and we would never know. They don't interact with light. They don't bounce off atoms. They barely notice the universe at all, which is exactly what makes them such a terrifyingly perfect dark matter suspect. But that's not where the axion story started. The origin goes back to a different mystery, one that made physicists uncomfortable for years. It's called the strong CP problem, and it has to do with the forces inside atoms. There's a theory called quantum chromodynamics, which describes how quarks and gluons stick together. The math says this force should break a symmetry called CP symmetry, basically a balance between matter and antimatter. And yet, when we look at actual particles, that symmetry holds up way too well. The theory predicts a slight wobble in the electric dipole of the neutron, but no one has ever found it. Not even a trace. So something must be cancelling it out. Something must be stepping in and fixing the math in the background. That's where the idea of the axion came from. It wasn't created to solve dark matter. It was invented to make quantum theory less broken. The axion would quietly tweak the strong force so the symmetry holds. No drama, no explosions. Just a ghost particle doing its job. But then things got wild. When physicists started calculating what axions would actually be like, they realized these particles wouldn't just fix the neutron problem. They'd be cold. They'd be stable. And there would be a lot of them. So many that they could account for the missing mass of the entire universe. Suddenly, a solution to one mystery crashed headfirst into another. A hypothetical particle created to patch a gap in nuclear physics might actually be the invisible glue holding galaxies together. And here's the part that gets truly creepy. If axions exist, they don't come in bursts. They come as a background field, a constant ocean of ghost energy soaking the cosmos. They wouldn't behave like other particles that clump and scatter. They would move as a smooth, uniform presence. That's why some scientists think we've never seen them. They're too gentle, too consistent, like the static hum of a universe running in the background, undetectable by normal means. But we're starting to get clever. There are experiments being built with magnetic fields strong enough to coax axions into revealing themselves. The idea is that under the right conditions, an axion could convert into a photon, a particle of light, not by force, not by collision, just by slipping through a magnetic field the right way. If even a tiny number of axions could be caught doing this, it would change physics overnight. There's also a bizarre twist involving black holes. Some theories suggest that if axions exist in the right mass range, they could interact with spinning black holes, draining their energy in a process called superradiance. That means some of the weird behavior we see near black holes might already be hinting at axions in the background. We just haven't realized it yet. And then there's the deeper possibility. If axions are real, they're not just another particle on the roster. They're a whole new form of matter. They'd be the first proof that the standard model of physics is incomplete in a way that actually touches the cosmos. They'd mean the universe has been running on ghost software all along. Fields we couldn't detect, forces we didn't understand, mass that was always there, hidden behind the curtain of light, and heat in atoms. And maybe the most beautiful part is that they were never meant to be found. Axions weren't designed to be dark matter. They were a quiet fix for a math glitch, an invisible nudge to keep the neutron balanced. And in solving that tiny, obscure problem, they might just end up solving one of the biggest cosmic mysteries we've ever faced. So maybe dark matter isn't exotic black holes or supersymmetric particles or extra dimensions. Maybe it's just axions, soft, silent, omnipresent particles drifting through the universe like ghosts, fixing what's broken, holding everything together, and reminding us that the strangest answers are sometimes hiding in the problems we weren't even looking at. Topological insulators. Most materials in the universe play by pretty straightforward rules. You pass electricity through a metal, it flows. You try that with an insulator like rubber or glass, and the current dies instantly. So we're used to thinking of things in these two camps, conductors and insulators, on or off, flow or block. But there's a third category, and it's one of the most bizarre things solid state physics has ever uncovered. It's called a topological insulator, and it completely rewrites how we think matter can behave. Here's what makes it strange. A topological insulator is completely dead on the inside. The bulk of the material behaves like an insulator. No flow, no movement of electrons, just pure blockage. But the surface, the outer skin of the material, is a different story. It behaves like a perfect conductor. Electrons on the surface move freely, smoothly, without resistance. The core stays shut down, but the boundary becomes alive. It's like the material is hollowing out its own rules, blocking electricity inside, but giving it a superhighway on the outside. Now that might sound like a simple gimmick, like a coating or some weird chemical trick, but that's not what this is. This isn't about atoms or impurities. It's about geometry. Topology is the math of shape, but not normal shape like triangles and squares. It's about deep structure. Properties that don't change even when you stretch or twist the object. Like how a coffee mug and a donut are technically the same in topology because they each have one hole. And somehow, that same kind of logic applies to quantum states in certain materials. When electrons move through a solid, they don't act like tiny marbles bouncing around. They follow quantum rules. They exist in allowed bands of energy. And those bands can be shaped by how atoms are arranged in the crystal. What physicists discovered is that in some very specific cases, the shape of those energy bands wraps around in a way that forces the edges of the material to behave differently than the inside. Not by accident, not by design, by necessity. The surface must conduct. It's protected. No matter how dirty the surface gets or how imperfect the material is, those edge states stay active. They're immune to scattering. They're locked in by math. And here's where things get wild. These edge states are not just protected. They're weirdly directional. Electrons moving along the edge of a topological insulator are often locked to their spin. That means an electron with spin pointing up goes one way, and an electron with spin pointing down goes the other. So even if you try to make them bounce backward, they don't. They're shielded from normal resistance. That's something no ordinary conductor can do. Even copper or gold loses energy as electrons bump into things. But on the surface of a topological insulator, the electrons just glide. Now imagine what that means for real-world tech. If you can build circuits out of this stuff, you're talking about electronics with almost no energy loss. Systems that stay cool, fast, and stable. Quantum devices that don't scramble when you breathe near them. And because the surface states are tied to spin, this opens up the world of spintronics, where we don't just use the charge of the electron, but its orientation to carry information. That's like doubling the alphabet of computing. But it gets even deeper. The same mathematics that describes these materials also connects to some of the most exotic ideas in physics. There are parallels between topological insulators and black holes, between their edge states and theories of the holographic universe. In some sense, these materials are like miniature laboratories for testing ideas about the fundamental nature of space, time, and entropy. They're not just useful. They're reflections of deeper laws. And here's the kicker. For decades we had no idea this stuff existed. We thought we understood materials. Then suddenly, in the early 2000s, experiments started finding things that shouldn't be possible. Materials where current flowed only on the edge, even when the inside was completely shut down. And it wasn't just one or two. Once the idea of topological phases caught on, physicists realized there were entire families of materials out there breaking these rules in spectacular ways. Insulators that behave like metals, metals that act like magnets, systems with no symmetry producing perfectly ordered flows. All of it comes down to topology. The idea that shape isn't just geometry. It's fate. You can't scrub away the behavior of a topological insulator without changing the entire structure of its quantum state. That's what makes it so robust. That's why it survives disorder, noise, and temperature shifts. It's not fragile. It's coded into the material's identity. So next time you think about matter, forget the binary rules of conductor and insulator. There's a third path, a middle ground where the inside and outside live by different laws, where the surface becomes a highway and the book becomes a wall, where geometry becomes electricity, and the only thing keeping the current alive is the way the universe twists in on itself at the quantum level. Because in a topological insulator, the surface knows something the inside never will, and that difference changes everything. Majorana Fermions. Let's say you take everything you know about matter and antimatter and just throw a wrench straight into the middle of it. Up to now, we've been taught that for every particle in existence, there's a shadow twin. That's how the universe keeps its balance. Electrons have positrons, protons have antiprotons. If they meet, they cancel each other out in a burst of pure energy. One is the mirror image of the other, equal and opposite, like a cosmic dance with rules baked into the floor. But now imagine a particle that breaks that symmetry. One that doesn't have a twin. It doesn't need one, because it is its own antiparticle. Not a pair, not a mirror, just one thing, perfectly balanced, completely self-contained. That's a Majorana Fermion. And this isn't just theoretical sci-fi. These particles could be real. They could already be affecting us in ways we haven't noticed. And if we find them, we're not just checking off another box in particle physics. We're unlocking a whole new layer of the universe. This idea goes all the way back to the 1930s, when an Italian physicist named Ettore Majorana proposed something outrageous. He realized that under the right conditions, the math describing fermions, the building blocks of matter, allowed for a version that didn't require an opposite, a particle that when flipped still looked exactly the same. And then, as if that wasn't spooky enough, Majorana vanished, just disappeared. No trace, no final statement, just gone. And all we had left was this mind, warping idea about particles that don't follow the usual rules. Now let's fast forward to today. Why does any of this matter? Because the more we study the universe, the more it looks like something is missing. Something subtle. Neutrinos, for example, those ghost-like particles flying through your body by the trillions every second, are acting suspicious. They're supposed to be like everything else, matter and antimatter, but some of their behavior doesn't fit. They might be Majorana particles in disguise. And if that's true, it could explain why the universe didn't just annihilate itself right after the Big Bang. It could be why there's something rather than nothing. But here's where things get even crazier. While high-energy physicists are trying to track these things in the cosmos, solid-state physicists have gone a different route. They're trying to build them. Not the actual particle, but a sort of echo. In ultra-cold lab setups with superconducting materials and fine-tuned magnetic fields, researchers have created quasiparticles that behave exactly like Majorana Fermions. These are not traditional particles, but combinations of electrons that, under the right quantum conditions, start acting like their own opposites. In other words, engineered versions of the real thing, and these lab-made Majoranas are doing something else that has scientists completely obsessed. They're ridiculously stable. In the world of quantum computing, that's the holy grail. Most qubits, which are the basic units of quantum information, fall apart the second anything touches them. Heat, noise, random atoms. But Majorana modes don't care. Their quantum information is spread out, topologically protected, meaning it can't be knocked out by local disruptions. This makes them prime candidates for something called topological quantum computing. Not just a better version of current systems, but a whole new kind of computer. A machine that runs on a logic deeper than silicon, storing data in a form that reality itself finds hard to corrupt. But we still don't know if we've seen a true Majorana Fermion. The lab setups are promising, but nothing is fully confirmed. No one has caught one floating freely in nature, and that opens up a question that cuts right through the heart of physics. Are we chasing something real, or just building clever illusions that mimic an idea? Either way, it's forcing us to rethink what a particle even is. And here's the deeper punch. If Majorana Fermions exist, they don't just solve a few annoying problems. They might rewrite the standard model itself. Right now, that model is the most accurate theory we've ever built. But it's incomplete. It can't explain gravity. It can't account for dark matter. It has no mechanism for why neutrinos have mass. Majorana particles could thread those needles. They might connect pieces we thought were unrelated. Ghost particles, cosmic asymmetry, stable quantum states. It all fits together if this one weird particle is real. And think about the symbolism. A particle that is both itself and its own opposite. A thing that doesn't need a partner to be complete. In a universe obsessed with symmetry and duality, that kind of balance feels almost poetic. Maybe nature doesn't always need a mirror. Maybe in some rare, strange cases, it can just fold back on itself and keep going. So we keep searching. In space. In the lab. In the patterns we don't fully understand yet. Because if we ever do find a true Majorana Fermion, it won't just be a new piece of the puzzle. It'll be a whole new frame for the picture. Emergent gravity. You know that feeling when you drop something and it hits the floor before you even process it? That invisible force pulling everything down. We call it gravity, and we've treated it like a fundamental truth of the universe for centuries. Newton said it's a force between masses. Einstein upgraded it to the bending of space and time, and for the longest time we've assumed gravity is just there, an essential rule baked into reality. But what if it isn't? What if gravity is not a force at all, but an illusion, a side effect, not real in the way we think? That's what the idea of emergent gravity is about, and once you hear it, you cannot unhear it. This theory flips the whole game board. Instead of treating gravity as a core feature of physics, it treats it like a symptom, a kind of quantum afterglow. Emergent gravity says that what we feel as gravity might actually come from entropy, the way information spreads and rearranges itself in the universe. Which sounds like science fiction until you realize it's rooted in one of the most powerful concepts in all of physics. The idea that space, time, and energy might not be fundamental. They might emerge from something deeper, something more abstract. To understand this, you need to zoom out. Think about thermodynamics. You heat up a pot of water, and the molecules start moving faster, not because there's a tiny fire god inside the water, but because millions of tiny interactions between atoms add up to something bigger. Temperature. Temperature isn't a thing on its own. It emerges from the collective behavior of particles. Same with pressure. Same with entropy. So what if gravity works the same way? What if it only exists because trillions of microscopic bits of information are being rearranged beneath the surface of what we call reality? This is where things get seriously weird. Physicist Eric Verlinde proposed a version of this in 2011 and then expanded it into a full theory. He suggested that gravity might be the result of entropic forces, systems naturally moving from order to disorder. Imagine the universe as a giant hard drive full of encoded data. Every particle, every atom, every black hole is storing and processing information. And that information wants to spread out. So when you drop an apple, what's really happening is that the system is adjusting to maximize entropy. The apple moves not because it's pulled down, but because the universe is reshuffling itself into a more probable state. You're not falling toward Earth. You're being sorted by statistics. And it's not just a thought experiment. In this model, space itself is like a hologram. Not a fake image, but a projection, a surface that encodes deeper data from another layer of physics. Gravity, then, is not an interaction between masses, but a thermodynamic response to how that data is distributed. It's like the wrinkles on a sheet. You don't need to understand each individual thread to see the overall shape. Now here's the kicker. This theory actually predicts the behavior of galaxies in ways that rival dark matter. We've known for decades that stars on the edges of galaxies move way too fast. The math doesn't add up unless there's invisible matter holding everything together. But emergent gravity claims that you don't need invisible matter at all. The laws of gravity just change slightly at cosmic scales because of how entropy works. That alone could rewrite everything we thought we knew about cosmology. Of course, this is controversial. A lot of physicists think emergent gravity is elegant but incomplete. It hasn't fully replaced general relativity or matched the precision of other models. But that's not the point. The point is, it offers a way of thinking that slices deeper than forces and masses. It forces us to question whether the stuff we call real is actually just emergent behavior. Whether what we experience as gravity is really just the universe playing out its statistical probabilities in the most efficient way possible. And think about what that means. It means that the force pulling you to the ground might not be fundamental. It might just be what happens when reality tries to process its own information. When disorder increases. When entropy does what entropy always does. And that raises a brutal question. What else is emergent? What else feels real but isn't? Is time itself just a trick? Is the flow of cause and effect just our limited perspective on some deeper order? Gravity used to be the most intuitive thing in the world. What goes up must come down. But emergent gravity whispers something far stranger, that what goes down might not be falling at all. It might just be reorganizing. And that the force we thought ruled the universe might be nothing more than the side effect of everything trying to forget where it came from. Noncommutative geometry, try to picture this. You're walking through space, not outer space, but space itself, the grid beneath reality. Up, down, left, right. It all feels smooth, continuous, clean. You move forward 5 steps, then 2 steps to the left, and you end up at the same spot whether you took the left turn before or after the 5 steps. Simple. That's the math we live in. Symmetry, structure. That's what our world is built on. But now imagine shrinking all the way down. Past atoms, past quarks, past the point where space even makes sense. Down there, that clean grid breaks. Space stops behaving, and suddenly the order of your steps matters. That's what noncommutative geometry is all about. The idea that space, at the most fundamental scale, might not follow the math rules we're used to. That space is not a smooth fabric, but a kind of quantum chaos where even the act of moving through it creates different outcomes depending on how you do it. It's not just strange, it's terrifying. Because if this is true, then the geometry of our universe is only an illusion held together by scale. It only seems normal because we're too big to see the weirdness underneath. Now here's the shock. This isn't just wild speculation. This idea comes straight out of quantum mechanics. In normal math, numbers commute. That means you can multiply them in any order and get the same answer. 2 times 3 is 6. 3 times 2 is 6. That's how our entire understanding of space has worked. But in quantum mechanics, certain operations don't commute. Measuring a particle's position before its momentum gives a different result than doing it the other way around. The sequence matters. And when you apply that logic to the fabric of space itself, things get wild. Noncommutative geometry says that the coordinates of space, the actual x and y positions of reality, might not commute either. That means if you measure the location of a particle and then its direction, you get a different result than if you do it in reverse. And if that's the case, then space is not a passive background, it's a dynamic player in the game. It's not just where things happen. It affects how they happen. It has memory. It has texture. This theory is not just some fringe idea. Mathematician Elaine Connes helped formalize it, and physicists have been exploring how noncommutative geometry could explain everything from the behavior of quantum fields to the nature of gravity. In fact, some researchers think this might be the key to merging quantum mechanics and general relativity. Right now, those two theories do not get along. Quantum physics says everything is fuzzy and probabilistic. General relativity says space and time are smooth and predictable. Noncommutative geometry suggests that both might be right, but only in different regimes. On large scales, space averages out and looks smooth, but up close, it's a storm, a mess, a tangled knot of non-commuting relationships. And here's where it gets crazier. If space doesn't commute, then space itself might be quantized. Not just the things inside it, but the structure of space. Tiny, indivisible units that you can't subdivide no matter how hard you try. That would mean there's a smallest possible distance in the universe. You could never zoom in closer than that. No infinite decimals, no perfect continuity, just a hard limit where geometry dissolves into algebra. And that brings up a weird consequence. If positions can't be precisely pinned down at that level, then location becomes a kind of suggestion. You don't exist in one exact place. You exist in a cloud of possible places, depending on how the rest of the universe interacts with you. Which sounds insane, until you realize it mirrors how quantum particles already behave. Noncommutative geometry might just be the missing language we've needed to describe the universe, when it's not pretending to be classical. It's already being used to build models of space where gravity emerges from deeper algebraic structures, where black holes are not just bends in space, but expressions of geometric uncertainty, where time itself might be a byproduct of the way space fails to commute cleanly. It's even creeping into string theory, where branes and dimensions start to blur into abstract mathematical operators. The implications are bottomless. And here's the most uncomfortable part. If noncommutative geometry is real, then the universe is not built on shapes and lines and graphs. It's built on relationships between things that can't be visualized. You can't map it with grids or measure it with rulers. You can only understand it through algebra, through symmetry breaking, through rules that don't play fair with intuition. So the space you think you're standing on might not really exist the way you believe it does. It might just be an approximation, a soft illusion emerging from something far more alien underneath. The structure of the universe could be less like a canvas and more like a quantum equation trying to express itself in 3 dimensions. Sakharov Conditions, time is weird. And I don't just mean in a poetic way. I mean it literally. You can run almost any law of physics backward and it still works. Flip the equations. Rewind the particles. Reverse every collision and every spin. The math still checks out. The universe doesn't care what direction you're playing it in. Forward or backward. The rules are the same. Except for one problem. Us, we exist. That right there is the break in the system. Because if time were perfectly symmetrical, there should be just as much antimatter as there is matter. There should be no arrow, no story, no direction. Just a flat, balanced mess. But that's not what we see. We see a universe that clearly picked a side. A universe with a before and an after. A universe that moves forward. And that crack, that irreversible tilt, is what the Sakharov conditions are trying to explain. This is not science fiction. This is the real bedrock of one of the biggest mysteries in cosmology. After the Big Bang, there should have been equal parts matter and antimatter. Identical twins in perfect symmetry, but instead, something broke the tie. Somehow, matter won. Antimatter vanished almost completely, and we were left with this strange imbalance: stars, planets, atoms, everything, all made from just one side of the coin. That's the asymmetry, and it shouldn't exist. Unless there were rules behind it, not accidents. Not miracles rules. In 1967, Soviet physicist Andrei Sakharov laid out exactly what kind of laws you would need to pull this off. And they are brutal. No soft explanations. No lazy shortcuts. If the universe wanted to break the symmetry between matter and antimatter, it had to meet 3 conditions. All 3. No exceptions. First, there has to be a way to create a difference between matter and antimatter. The universe needs a built-in bias, a preference. Some kind of particle interaction that doesn't treat matter and antimatter equally. This is called baryon number violation. It's a fancy way of saying that particles must sometimes be created or destroyed in ways that favor one side over the other. Without this, the scales would always reset to 0. Balance would always return. Second, the system has to break a rule called CP symmetry. That's short for charge and parity. And it basically says that if you flip a particle into its mirror image and reverse its charge, it should still behave the same way. The universe, in theory, should not care if you're looking at it forward or mirrored, positive or negative. But we now know that's not always true. Certain particles decay in ways that slightly violate this symmetry. But it's real, and it cracks the door open just enough for matter to slip ahead. Third, and this is the most ruthless part, the universe must fall out of thermal equilibrium. Everything has to be in chaos. Because if the energy levels were perfectly even, no matter what little biases existed, they would get wiped out. You'd have no way to preserve the imbalance. So the early universe had to be hot, expanding, unstable. In other words, it had to be exactly what the Big Bang gave us. A violent burst of pure entropy that provided the perfect stage for those 3 conditions to play out. Now here's the twist. Even though these conditions seem cold and mathematical, they carry enormous emotional weight. Because they suggest that the reason we exist is not random. It's not luck, it's structure. We are here because the universe followed very specific, very brutal instructions in its first moments. It allowed symmetry to break. It allowed time to favor a direction. It allowed matter to beat antimatter. Not because it had to, but because the laws allowed it, and it gets deeper. The Sakharov conditions don't just explain the imbalance. They hint at the nature of time itself. Because if everything was symmetrical, there would be no forward, no history, just stasis. But because the universe violated those symmetries, it created an arrow. One direction, one path. It's not just about physics. It's about narrative. The universe telling its own story in one irreversible line. But here's the real mystery. We still don't fully know what mechanism caused that first condition, the baryon number violation. We have ideas, grand unified theories, exotic particle decays, hints from neutrino behavior. But no one has seen it happen directly. It's still a ghost in the equations. Something that had to have happened, but left no clear trace. Like a crime scene with no fingerprints, only broken glass. Which means the deeper we go into this, the more it feels like we're chasing a memory, trying to reconstruct the moment when reality chose sides. And that leads to a haunting possibility, that time itself is not fundamental, but emergent, that it only exists because the early universe was just unbalanced enough to create it. So we dig, through particle physics, through cosmology, through the tiniest violations in the decays of Kahns and B. Masons, because if we can find the exact place where the Sakharov conditions were met, we won't just understand why there is something instead of nothing. We'll understand why time moves forward at all. Preons, you know what we've been told since we were kids. Everything is made of atoms. Then you grow up a little and find out, oh wait, atoms are made of protons, neutrons, and electrons. Then you go further and find out protons and neutrons are made of quarks, and that's where the textbooks usually stop. Quarks and electrons are the end of the road. The foundation. The raw ingredients of all matter. That's the official story. But there's a growing suspicion in physics that this still isn't the bottom layer. That quarks themselves might be built out of something even smaller, something deeper, something more fundamental. Enter preons. Preons are hypothetical particles that could be the building blocks of everything we currently think of as fundamental. They are the secret ingredients behind quarks and leptons, the ghost beneath the surface. And if they exist, then the entire structure of the Standard Model, our best theory of how particles behave, is not the end of the road at all. It's just another layer in a much deeper system. Now here's the wild part. There's actually a good reason to think we might be missing something. Because when you look at the Standard Model with clear eyes, it starts to feel messy. We've got 6 kinds of quarks, 3 generations of leptons, a whole zoo of particles with no obvious pattern. It works, but it feels more like a chart from a science fair than a unified theory. Why do particles come in families? Why do they have such bizarre masses? Why is the electron so light while the top quark is a literal monster? None of it makes clean sense. Unless all of those particles are composites, like atoms made of protons or molecules made of atoms. Maybe quarks and electrons are made of preons. That would mean nature has tricked us again. It gave us something that looks fundamental, but isn't. It gave us simplicity that hides complexity. Just like people once thought atoms were indivisible. Just like they once thought the Earth was the center of the universe. And we've been here before. Every time we've claimed to reach the limit, the universe has laughed and pulled back the curtain. Now, some of the earliest preon models came out in the 1970s and 80s. Back then, physicists were looking for patterns in the chaos, mathematical structures that could explain why quarks and leptons exist in such specific arrangements. They found hints, not proofs, but enough to raise eyebrows. What if, instead of 24 fundamental particles, there were just 2 or 3 types of preons, arranged in different combinations to make the particles we observe, like how a handful of Lego bricks can build thousands of different shapes? But here's where it gets complicated. Preons would need to be held together by forces even stronger than the ones we know, stronger than the strong force that binds quarks inside protons. We don't know what those forces are. We've never seen them. And because preons are theorized to exist at energy scales far beyond anything we've been able to reach, we can't smash particles hard enough to reveal them. Yet, some physicists think the key might lie in unification, the idea that at super high energies all the fundamental forces merge into one. If that's true, then maybe quarks and leptons are just different expressions of a deeper field. Maybe preons are the pieces of that field, carriers of a hidden logic that binds everything together, but only reveals itself when conditions are just right, like fossils locked in stone, waiting to be cracked open. Now here's where the tease turns deadly. If preons exist, they could solve multiple mysteries at once. They could explain the mass hierarchy problem. Why particles have such dramatically different weights. They could offer clues about dark matter. If some preon combinations are stable but invisible to our detectors, they might even bridge the gap between the Standard Model and gravity, something string theory has struggled with for decades. There's always a but. We haven't seen them. No preon has ever been directly detected, and if they are real, they are hiding extremely well. Some people argue they are unnecessary, that the Standard Model, messy as it is, still works brilliantly. And from a pragmatic view, if your theory doesn't make new predictions or show up in experiments, it might just be pretty math. But others, they see a pattern that's too weird to ignore. They see echoes of something deeper. They see a universe that might not be built from quarks and leptons after all, but from an even smaller alphabet we've only just begun to guess at. And if that's true, then everything we call matter is just a structure built from invisible architecture. A symphony we've only heard the surface of, and someday, maybe, when we crack open the next particle or collide atoms with enough energy to light up the truth, we'll see it, the actual building blocks, the Preons whispering beneath reality, shaping everything while staying perfectly hidden. Vacuum birefringence. Think about what we call empty. Just nothing. The void between stars, the gap between atoms. Space that contains absolutely zero particles, no dust, no air. Dead, flat, meaningless vacuum. But what if that emptiness isn't actually empty? What if even in the blankest parts of the universe, something is quietly happening? And not just something small. Something that can twist light. Something that can bend photons without touching them. This is where things start to feel supernatural. It's called vacuum birefringence. And no, this is not some obscure lab quirk. This is a real prediction from quantum electrodynamics, one of the most precisely tested theories in all of physics. And it says that in the presence of an extremely strong magnetic field, like, we're talking neutron star, level strong, even a perfect vacuum starts acting like a crystal. It starts to mess with light in a very specific, very strange way. You send a beam of light through this magnetic vacuum, and instead of just passing through, like it would through clean air, the light splits. It behaves differently depending on its polarization, the direction in which it's vibrating. One component moves faster, the other slower, as if the vacuum suddenly grew an attitude. As if it decided, I'm going to treat this part of the wave differently than that one. That's birefringence. Usually you only see this kind of behavior in weird transparent solids like calcite or certain plastics, but here it's happening in space. Raw empty space. Now, this is where it starts to melt your brain, because a vacuum is not supposed to do anything. It's the absence of matter, the background nothingness. But quantum theory says no. Even in a vacuum, there's still activity. There are still fluctuations, virtual particles popping in and out of existence, electron-positron pairs appearing and vanishing in trillionths of a second. You can't see them directly, but they affect how other particles behave. They leave fingerprints. So when a strong magnetic field hits that vacuum, those virtual particles align. They polarize. They create a direction in space where there wasn't one before. And suddenly, light is no longer free. It's forced to choose a path. And depending on the angle of its polarization, it either moves freely or gets slightly delayed. Light, the fastest thing in the universe, gets bent by literally nothing. That should not be possible. But it is. This was predicted back in the 1930s. It took nearly a century before we had any chance of detecting it. Why? Because the magnetic fields required to trigger vacuum birefringence are outrageously strong. You'd need fields 1 billion times stronger than anything we can generate on Earth. But nature gives us tools, and those tools are magnetars. Magnetars are a special kind of neutron star. They're so dense that a teaspoon of their matter would weigh as much as Mount Everest. But more importantly, they have magnetic fields so intense they can warp the vacuum around them. And in 2016, a group of astronomers used a powerful telescope in Italy to observe visible light coming from the surface of a magnetar. And what they saw? Polarization, in a way that matched the prediction. It wasn't conclusive proof, but it was one of the strongest hints that vacuum birefringence is real. Just pause on that for a second. Light, traveling across the vacuum of space, being twisted ever so slightly by a magnetic field acting on virtual particles that don't even exist long enough to be seen. We are watching nothing do something, and that something is bending one of the fundamental forces of the universe. Here's what makes it even more insane. This means that the vacuum is not neutral. It's not a passive stage where reality unfolds. It's a player. It has structure. It has behavior. And under the right conditions, it starts acting more like a medium, almost like a fluid with rules, rather than a true absence. That completely flips how we think about emptiness. Space isn't empty. It's potential waiting to be triggered. And there's more coming. The next generation of powerful lasers and telescopes might finally allow us to observe this directly, not just around magnetars, but under controlled conditions. If we can confirm vacuum birefringence with precision, we won't just prove another part of quantum electrodynamics. We'll open a window into the nature of the vacuum itself, into how reality behaves when nothing is there to define it, because maybe space is not the void between things. Maybe it is the thing, a living, active, fluctuating entity, always on, always reacting, even when it seems like there's nothing there. And that changes everything we thought we knew about the foundations of the universe. Superfluid vacuum theory, brace yourself, because this one is going to punch a hole right through your idea of what space even is. Forget the usual idea of the vacuum. That cold, empty nothingness stretching across the universe. No particles, no structure, just infinite silence. Now throw that away. Because there's a theory that says the vacuum, the very thing we thought was absence, might actually be a fluid. Not metaphorically, literally, a superfluid. Let that hit for a second. What we think of as empty space might be a physical substance, and not just any substance, a superfluid, something with zero viscosity, something that flows without resistance, something that cannot be stirred, something that behaves more like a perfect liquid than nothing at all. That is the core idea behind superfluid vacuum theory. It sounds like science fiction, but here's the weird thing. It fits, like disturbingly well. Superfluid vacuum theory proposes that space itself is made of a quantum fluid, and the particles we think of as fundamental, photons, electrons, quarks, they're not the building blocks. They're just excitations, tiny ripples, waves moving through that underlying fluid, just like sound waves in air or ripples in water. Which means everything you think is solid and real might just be patterns in an invisible ocean that fills the universe. Let's talk about superfluids for a second, because they're real. If you cool helium down close to absolute zero, it becomes a superfluid. You can pour it into a container, and it will crawl up the sides and spill over the edge without any force applied. It flows forever without slowing down. It behaves in ways that defy gravity and thermodynamics. It's like the rules break down completely. Now imagine that same kind of bizarre fluid, but spread across all of space. That's what this theory is suggesting, that beneath all the equations and forces and particles, there's a hidden layer, a continuous medium, and that medium behaves like a superfluid with its own properties. Not empty, not void, but structured, with density, with motion, with the ability to ripple and swirl and carry information. Here's where it gets even crazier. In this framework, gravity itself might not be a force in the traditional sense. Instead of being the curvature of space-time like general relativity says, gravity could just be the result of how mass disturbs the vacuum fluid. Like dropping a stone into a pond, the fluid moves. The ripples spread. Other objects follow those ripples. What we call gravity might just be the fluid reacting to mass, which turns our entire understanding of motion and attraction on its head. And this could help explain some really annoying problems in modern physics, like why quantum mechanics and general relativity don't get along, or why gravity is so insanely weak compared to the other forces. If space-time is just a fluid, then maybe the tension between quantum fields and curved geometry disappears. Maybe we've been trying to stitch together two maps of the same terrain, not realizing the terrain itself is liquid. It also gives us new ways to think about dark energy and dark matter. Maybe they're not mysterious things hiding in space. Maybe they are properties of the fluid itself, pressure differences, flow patterns, anisotropies we haven't mapped yet. Instead of being exotic matter or ghost particles, they could be fluid behavior we just haven't interpreted correctly. Now, critics will tell you this is just mathematical poetry, that it's pretty but untested. And they're right. There's no smoking gun yet. No experiment has definitively confirmed the vacuum is a superfluid. But there are hints. the behavior of the cosmic microwave background, certain features of black hole thermodynamics, patterns in particle physics that seem too elegant to be random. There's something there. And it gets even more intense when you realize this theory doesn't just explain physical stuff. It might explain the limits of information itself, like why there's a cosmic speed limit, why particles behave probabilistically. If the vacuum is a superfluid, then quantum mechanics could just be describing the turbulence, the froth on top, and all those strange quantum effects, entanglement, uncertainty, superposition, might just be how waves behave in a medium we cannot touch. Now take a breath and really consider that. The most foundational things we think we know, energy, particles, spacetime, gravity, might all be illusions, not fake, just emergent. Like weather is not a thing, it is just what air does. What if particles are not things? They are just what the vacuum does. And we're still at the beginning. New theoretical models are trying to predict how this superfluid vacuum would behave under extreme conditions. Inside black holes, at the start of the Big Bang. And if we can find those conditions in nature, if we can observe something the standard model cannot explain, but this theory can, we could be standing at the edge of the next great physics revolution. We are not floating in empty space. We are swimming in something deeper, something smoother, something stranger than anything we were ever taught. Anyon particles, you've probably heard this before. All particles in the universe fall into one of two camps, fermions and bosons. Simple fermions make up matter. Bosons carry forces. Every particle, from electrons to photons to quarks to gluons, fits into one of those two categories. But that rule only applies in three-dimensional space. Up, down, left, right, forward, back. The world we live in. But if you flatten everything, strip reality down to just 2 dimensions, a third type of particle shows up. Something that breaks the rules. Something that cannot exist in our everyday world. These are anyons. And they're not just theoretical toys anymore. We've actually seen them. They are real. And they're weirder than anything else on the particle chart. Here's the thing about particles. In our 3-dimensional world, when 2 particles of the same type are swapped, nothing observable happens. It's a symmetry thing. Fermions, like electrons, just pick up a minus sign in the math. Bosons stay the same. But either way, the swap leaves the physics unchanged. Now in 2 dimensions, the math opens up a weird loophole. When you exchange 2 particles in a 2-dimensional space, the result can be something in between. Not plus, not minus, but a phase shift, a twist in the wave function that depends on how you swapped them. And that means these particles don't behave like anything else. They're not fermions. They're not bosons. They're something new. That's what we call anyons. And yes, they only show up in flatland, not in theory, in actual physical systems that behave like 2-dimensional planes, like extremely thin layers of semiconductor material cooled down near absolute zero. Under those conditions, quantum mechanics reveals its stranger side. And suddenly, you get collective excitations that act like particles, but with totally alien behavior. Let's pause on that for a second. These are not individual particles like electrons. They're quasi-particles, emergent phenomena, meaning they don't exist by themselves. They arise from the collective dance of electrons trapped in 2 dimensions. But once they show up, they behave like real particles. They carry charge. They interact, they move, and most importantly, they remember how they were moved. This is the most mind-bending part. Anyons have something called braiding statistics. That means when you move one anyon around another, it doesn't just pass by and forget about it. The system keeps track of the path. Not just the position, but the history. It's like the fabric of space in that flat layer is being twisted and tied every time these particles move. And if you do a full loop, take one anyon all the way around another and back to its original spot, the quantum state of the entire system changes in a measurable way. That sounds abstract, but it's not just math. It's been measured. In 2020, Researchers in the US and Europe used a carefully built experiment in a quantum Hall system to braid anyons. And when they looped one around another, the interference pattern shifted. Exactly as predicted, that phase shift wasn't just theory anymore. It was reality behaving in a way that would be impossible in 3 dimensions. Now here's why this matters. That braiding behavior, the memory, the twists in the quantum state, makes anyons incredibly powerful candidates for quantum computing, because normal quantum bits are extremely fragile. They can decohere just from tiny vibrations or noise in the environment, but anyon-based systems store information in the topology of their braiding, the shape of their paths, not just their positions. That makes them much more stable, much more resistant to errors. This is called topological quantum computing, and if we can master it, it could be the key to building quantum computers that actually work long-term. But let's go even deeper. This whole idea challenges what we even mean by a particle. We used to think of particles as tiny, indivisible bits of matter, like miniature marbles. But anyons don't fit that picture. They don't even exist until the conditions are just right. They're born out of the collective behavior of a system. They emerge when electrons and magnetic fields and temperature line up perfectly. So what does that say about the other particles we take for granted? Are they truly fundamental? Or could they also be emergent? Could reality itself be the result of a deeper, hidden structure? Because if a flat 2-dimensional sheet can produce particles with entirely new statistics, what else is possible in higher or lower dimensions? What happens at the edge of a black hole, where space itself is warped into a kind of 2-dimensional hologram? What happens inside materials we haven't even invented yet? Anyon particles are like cracks in the wall, little leaks in the perfect symmetry we thought the universe followed. They prove that the behavior of matter depends not just on what it's made of, but on where and how it exists. And maybe, just maybe, our 3-dimensional world is hiding an even stranger set of rules, just waiting to be uncovered. Gravity as an entropic force. Time to flip the one force you thought you understood. Gravity, the most familiar thing in your entire life. It keeps your feet on the ground, holds the moon in orbit, shapes galaxies, feels so basic, so real, so unavoidable, like it's just there. But what if I told you gravity might not be a force at all? What if it's not pulling you down but pushing you, statistically? Like heat, like entropy. What if gravity is not a fundamental law, but just the universe doing bookkeeping? This is not science fiction. This is a real idea backed by serious physics. It's called gravity as an entropic force. And once you see how it works, it starts eating away at everything you thought was solid about the universe. Let's back up. Entropy is a measure of disorder. It's the reason why your coffee cools down over time, not up. It's why eggs break and never unbreak. It's why time only moves forward. Because the universe tends to increase entropy. It wants more possible configurations, more randomness, more ways for particles to rearrange themselves. That's the arrow of time, and we usually keep that idea far away from gravity. But maybe we shouldn't. Picture this. You've got a particle moving near a massive object, like a star. According to traditional physics, gravity pulls it. Simple. But what if that motion is actually being caused by entropy trying to increase? The particle gets nudged, not because something is tugging on it, but because the number of possible microscopic states goes up when it moves closer to the mass. The universe favors that shift. So it happens. No pull. Just probability. That idea was proposed by physicist Erik Verlinde. He argued that gravity is not fundamental. It emerges from changes in entropy, changes in the number of ways particles can be arranged. Just like pressure is not a thing you build into a molecule, it's something that emerges from trillions of molecules bouncing around. Gravity, in this view, is the same kind of thing, not a cause, a consequence. Now, if that sounds too wild, think about this. Gravity has always been the odd one out. Quantum mechanics covers 3 of the 4 fundamental forces: electromagnetism, the strong force, the weak force. But gravity refuses to fit. We have zero working theory of quantum gravity. Every attempt to quantize it has failed or ended in infinities. That alone should be a clue. Maybe we're trying to quantize something that was never fundamental to begin with. And here's where the heat part comes in. Entropic forces always arise from temperature. Think about a stretched rubber band. It snaps back not because it wants to, but because there are more microscopic ways for it to be loose than tight. Heat is just a measure of those microscopic motions. So if gravity is entropic, then temperature must play a role. Now imagine space itself has a kind of temperature, a kind of information structure. And when a particle moves in that space, it follows the path that increases entropy. Just like heat flows from hot to cold. That path looks like a gravitational trajectory. It's not being pulled. It's falling into a more probable configuration. Gravity, in this view, is the shadow cast by entropy. This idea also offers a fresh way to explain dark matter. Valendi proposed that the missing gravity we observe in galaxies, the stuff we usually blame on invisible matter, might just be a side effect of entropic gravity on cosmic scales. We think something must be adding extra pull, but maybe the pull isn't real. Maybe it's the entropic structure of space reacting to the distribution of mass. We don't need dark matter. We need a better model. Now, this theory is still being tested. It hasn't replaced Einstein's general relativity, but it's one of the few modern ideas that actually tries to tie gravity to thermodynamics and information theory, two areas that already explain a ton of other mysteries. And it syncs up in weirdly elegant ways with black hole physics, like how a black hole's surface area is related to its entropy, or how Hawking radiation makes black holes slowly evaporate as they lose information. If gravity is entropic, then black holes make perfect sense. They're not objects. They're maximal entropy states, the ultimate statistical traps, and space-time itself becomes a kind of medium for information flow. Less a fabric, more a ledger, recording who went where and why. Now sit with that, because it means the gravity you feel when you drop your phone might just be the universe running the numbers. Particles following the most statistically favored paths, not pulled, not pushed, just chosen by entropy. And the implications are massive. If gravity is not fundamental, then maybe space and time aren't either. Maybe they emerge too, from deeper, more abstract layers of information. Maybe the universe is not built on stuff, but on probability. Black hole thermodynamics. You know what's terrifying about black holes? It's not just that they crush stars or eat light. It's not even the idea that time stops at the edge. The real nightmare begins when you realize black holes are hot, not cold, hot. They radiate energy. They leak, they die. That is not something we were supposed to know. That one detail cracked open physics in a way we're still trying to understand. For the longest time, black holes were treated like giant cosmic dumpsters. Stuff falls in. Nothing comes out. No light, no information. Just a silent abyss with an event horizon, the point of no return. But that idea started to fall apart when physicists asked a simple, dangerous question. What happens if you throw entropy into a black hole? Entropy is not just a fancy word for disorder. It is the currency of thermodynamics. It measures how many microscopic ways a system can be arranged. The more entropy something has, the more it resists being fully known. And here's the thing. When you burn a log or melt ice, entropy goes up. Always. The universe demands it. So what happens when you drop something full of entropy into a black hole? Does the entropy just disappear? That would break one of the most sacred laws in physics. Enter Jacob Wittgenstein. He proposed that black holes must have entropy, and that entropy is related to the surface area of the event horizon. Not the volume, the area. That idea was nuts at the time. It meant the black hole's information content was somehow smeared across its outer edge, not buried deep inside. But then Stephen Hawking took it further. He realized that if black holes have entropy, they must also have temperature. And if they have temperature, they cannot be perfectly black. They must radiate. He ran the numbers and found something wild. Black holes actually emit a faint thermal glow, now called Hawking radiation. The colder the black hole, the bigger it is. The hotter it gets, the smaller it becomes. Over billions of years, it shrinks, it evaporates, it dies. That one prediction ripped through physics like a bolt of lightning. Because now black holes were not just cosmic sinkholes. They were thermodynamic objects. They followed the same laws that govern steam engines and ice cubes. The same laws that power your coffee maker now ruled over collapsed stars. Let that sink in for a second. A black hole, this monstrous gravitational beast that warps space and time, is also a thermodynamic system. It has temperature, it has entropy, it obeys the second law. And somehow, its entropy is directly proportional to its surface area divided by something called the Planck length squared, which is unimaginably tiny. So the total number of microscopic states a black hole can have is finite. You could, in theory, count them, which means even black holes are not truly unknowable. They just look that way from the outside. This led to something even crazier. The holographic principle. If the information about everything that falls into a black hole is stored on its surface, not its interior, then maybe our entire universe works the same way. Maybe the deepest laws of physics don't live in volume. Maybe reality itself is projected from a two-dimensional surface. That is not a metaphor. That is a literal possibility now being explored in string theory and quantum gravity. Black hole thermodynamics also cracked open the information paradox. If black holes evaporate, and if Hawking radiation is just random thermal noise, then all the information about what fell in is lost. And that is a problem, because quantum mechanics says information can never be destroyed. So either black holes break quantum theory, or Hawking radiation is not truly random. Maybe it carries a hidden code. Maybe the black hole's last dying breath whispers every secret it ever consumed. Slowly, subtly, across time. That question is still unresolved. It is one of the most important puzzles in theoretical physics, because depending on how it's answered, we may need to rewrite either gravity or quantum mechanics from the ground up. And here's the part that always messes with people. The entropy of a black hole is unimaginably huge. A single black hole the mass of the Sun has more entropy than the entire observable universe, filled with gas and galaxies. That tells you something profound. These things are not just gravitational prisons. They are the densest hard drives in the cosmos. They know something. They remember. So when you hear the words black hole, do not think emptiness. Do not think silence. Think heat. Think chaos. Think thermodynamic pressure. These monsters are not dead zones. They are burning with secrets. And when they vanish, those secrets do not go quietly. Schild's ladder. Imagine trying to explain curved space-time without using calculus. No integrals, no derivatives, no coordinates even, just raw geometry. Sounds impossible, right? But that's exactly what Schild's ladder sets out to do. And the crazy part is, it works. This simple geometric trick lets you measure the curvature of space, time using nothing but straight paths and relationships between points. No math degree required. Just some imagination and a bit of nerve. The setup is deceptively basic. Picture space-time as a smooth, stretchy fabric. Now take one point on that fabric and call it A. Draw a straight path from A to a nearby point B. In physics terms, that's a geodesic, the path that light or a free, falling object would naturally follow through space-time. Then from B, draw a second geodesic in the same direction as the first. You're now walking in a straight line through curved space. Here's where the ladder begins. From the original point A, draw another geodesic that connects to the end of that second line. You've now formed a little triangle of geodesics. 3 straight paths connecting 4 points. But in curved space, something strange happens. That triangle does not close perfectly. The final leg of the path misses its mark, and the gap between where you expected to land and where you actually end up is a measure of curvature. That gap is the magic. It tells you that space, time isn't flat. In flat space, like a piece of paper or an empty room, parallel lines behave nicely. Angles add up the way they're supposed to. shapes close themselves. But in curved space, everything gets weird. Parallel lines can converge or diverge. Triangles can have more than 180 degrees. And if you keep stacking these geodesic triangles, the mismatch builds up into a full-blown ladder. Schild's ladder. Each rung of the ladder is a tiny experiment in space. Time a way of asking, is this region flat or curved, and by how much? You never need to calculate anything directly. No tensors, no equations. The curvature shows up through pure geometry, through how shapes deform when you build them step by step. And it's not just a clever trick. Schild's ladder actually reproduces the same information that lives inside Einstein's field equations, the math that describes how mass and energy bend space, time. But instead of relying on continuous fields and smooth calculus, Schild's ladder builds curvature out of relationships. It's local, it's visual, and in a strange way, it's more fundamental. Because here's the deep insight. At the smallest scales, space, time might not be smooth at all. In the quantum realm, the idea of a continuous, infinitely divisible space breaks down. Instead, many physicists believe the fabric of reality is discrete, like pixels on a screen, little chunks of geometry stitched together by interaction. So our standard tools, derivatives, continuous functions, all the stuff calculus relies on, might not apply anymore. That's where Schild's ladder becomes more than just a geometry toy. It becomes a serious contender for how we might reconstruct gravity in a quantum universe. It works without smoothness. It plays nicely with the idea of causal sets and loop quantum gravity, the kind of frameworks that try to build space, time from discrete events or networks of relationships. What's even more beautiful is how intuitive it feels once you see it in action. Take 2 points. Draw a light path. Step forward, connect back. See the shape twist. That's it. The curvature isn't something abstract anymore. It becomes visible. You can almost feel it. The way space, time is nudging things around, bending paths that should be straight, distorting the rules of basic geometry. And in that distortion lies gravity. Because in general relativity, gravity isn't really a force. It's just curvature. Things follow the straightest paths they can. It's just that the straightest paths are bent by mass and energy. Schild's ladder makes that feel real. It shows you how bending appears without needing to talk about force at all. Now zoom out for a second. Think about what this means. If we can build curvature without coordinates, without fields, without even needing a traditional space, just from the relationships between geodesics, then maybe that's what space, time really is underneath it all. A web of paths, a structure of interactions, not a smooth stage things move on, but something built up entirely from how things move in relation to each other. This flips the whole concept of geometry on its head. We usually think of space as the thing we draw shapes inside of, but Schild's ladder suggests maybe shapes come first. Maybe space is just the story geometry tells when you give it time to unfold. And who knows, maybe the real theory of quantum gravity, the one we've been chasing for decades, won't be written in dense equations on a chalkboard. Maybe it will look more like a ladder. Just a sequence of light paths, twisting through a structure too small to see, but too important to ignore. Virtual particles. Let's talk about something that sounds made up but absolutely is not. Imagine a particle that is born, lives, and dies in less than a blink, so fast that it never really exists in any traditional sense. It just flickers into being and then vanishes. Nobody sees it. No one measures it. But it still manages to mess with the real world. It pushes objects. It bends light. It even messes with the structure of atoms. These are virtual particles, the ghosts of quantum mechanics. And the weirdest part is empty space is full of them. You heard that right. Empty space is not empty, not even close. What we call the vacuum, that so-called nothingness between stars and planets and particles, is actually boiling. It's buzzing with activity. Virtual particles are popping in and out of existence constantly, and it never stops. The vacuum is a storm, just invisible. Now here's the twist. Virtual particles aren't like the particles we usually talk about, the ones that make up atoms or bounce off each other in particle accelerators. These are different. They're unobservable. They don't follow the usual rules. They exist purely because quantum mechanics allows them to. They borrow energy from nothing, like they're taking a loan from the universe. And as long as they pay it back fast enough, the universe looks the other way. That is the loophole. That is how quantum uncertainty becomes reality. And the math backs it up. In quantum field theory, particles are just tiny vibrations in fields that stretch across the universe. What we think of as a particle, like an electron or a photon, is really just a ripple in a particular field. But even when the field is in its lowest energy state, its so-called vacuum state, it still has fluctuations. Those fluctuations are the source of virtual particles. They're not real in the sense that you can measure them directly, but they are real in the sense that they have measurable effects. One of the most mind-blowing examples of this is the Casimir effect. Take two metal plates, place them very close together in a vacuum, and hold them still. Nothing should happen, right? But something does. The plates actually start to move toward each other. Not because of gravity, not because of static charge, but because virtual particles are being squeezed out of the gap between them. The vacuum outside the plates has slightly more energy than the vacuum inside, and that difference creates a tiny pressure. That is the quantum vacuum at work. That is virtual particles reaching into the real world and pushing, and it gets even crazier. Virtual particles are responsible for something called vacuum polarization. When a charged particle like an electron sits in empty space, it's not really alone. It is surrounded by a cloud of virtual particles that blink in and out of existence and momentarily shield or amplify its charge. So what you think is the strength of an electron's electric field is actually the sum of both the electron and the ghosts swirling around it. Even the very definition of charge is shaped by particles that don't exist. And then there's Hawking radiation. This is where things hit another level. Near the edge of a black hole, virtual particles can appear as pairs, one with positive energy and one with negative. Normally they'd cancel each other and disappear. But if one of them falls into the black hole and the other escapes, the escaping particle becomes real. That escaping particle is Hawking radiation. It slowly drains energy from the black hole. Over trillions of years, it can even cause the black hole to evaporate completely. So yes, virtual particles can literally kill black holes. Now here's the part that messes with your intuition. You cannot measure a virtual particle directly. You can't catch one. You can't isolate it. The moment you try, it either becomes a real particle or it vanishes. But we know they're there because their fingerprints are all over the universe. The forces between particles, the energies of atoms, the corrections in every quantum equation, all of it has virtual particles baked in. So when people ask if virtual particles are real, the answer is both yes and no. They're not real like a baseball or a proton, but they are real in the sense that without them, nothing in physics makes sense. They're like backstage hands in a play, unseen, uncredited, but absolutely running the show. And maybe the strangest thing of all is this. These phantom particles are everywhere. Right now, around you, inside you, through your body. Trillions of virtual particles are flickering into and out of existence. They don't care about matter. They don't care about time. They're the quantum static of reality, the hum beneath the silence. What we call empty might be the most active thing in existence. Torsion fields. So you know how we usually imagine gravity as the bending of space-time, like this invisible fabric curving around a planet or a star. That's Einstein's thing. But what if space, time could do something even weirder than bend? What if it could twist? Yeah, not stretch, not compress, but actually twist on itself, like wringing out a wet towel. That's where torsion fields come in. And if this is the first you're hearing of it, buckle up. Because this idea flips our understanding of the universe sideways. Let's rewind for a second. In Einstein's general relativity, gravity is geometry. Mass and energy tell space, time how to curve, and that curvature tells objects how to move. But the thing is, that model only uses one part of geometry, curvature. It completely ignores something else, torsion. In basic geometry, curvature tells you how much a surface bends. But torsion. A torsion tells you how much something twists as you move along it, like a spiral staircase. The steps don't just rise, they rotate. That kind of twist is completely missing from Einstein's picture of space, time. But in more advanced geometric theories, like Einstein, Cartan theory, torsion is not just possible, it's essential. Here's where it gets wild. In the Einstein-Cartan model, every point in space, time can have not only curvature, but also torsion. That twist isn't caused by mass. It's caused by spin, actual spin, like the intrinsic angular momentum of particles. Every electron, every proton, every neutron, they all spin, even if they're sitting still. And according to these models, that spin can twist the fabric of space, time in a way that regular general relativity just doesn't account for. So now you've got two kinds of distortions happening. Mass bends space, spin twists it, and together they might create entirely new gravitational effects. Not just the stretching we associate with gravity, but a kind of torsional ripple, a spiral-shaped influence that could, under extreme conditions, show up in the real world. And by extreme, I mean early universe, near the Big Bang kind of extreme. Because torsion fields are thought to be incredibly weak. So weak, in fact, that we don't notice them in our everyday universe. But at the beginning of time, when everything was dense and chaotic and spinning like mad, torsion could have mattered a lot. It might have prevented singularities, those infinite density points we hate so much in black hole physics. In some models, torsion acts like a repulsive force at super high densities. So instead of a singularity at the Big Bang, you get a bounce, a rebounding universe, a before and after. Yeah. Some torsion-based models suggest the Big Bang wasn't a beginning, but a rebound. A crunch followed by an expansion. Space didn't just blow up into existence. It twisted its way back from a previous phase. That kind of idea turns the arrow of time into a loop. Now here's a mind bender. If torsion fields are real, then everything you do, every time your particles spin, every time you so much as blink, you're twisting space-time. Just a little. Not enough to measure, not enough to feel. But it's there, and if enough spin is concentrated in one place, who knows what kind of effects might ripple out. It raises questions about rotational fields, frame dragging, and maybe even quantum gravity. Some physicists even toy with the idea that torsion could explain dark matter or dark energy. That the missing mass we're looking for in galaxies might not be missing at all. It might just be hidden in the geometry. Not in the bending of space, time, but in its twisting. Invisible to our standard models, but baked into the structure of the cosmos. Of course, none of this is settled science. Torsion theories are still speculative. Mainstream physics hasn't embraced them with open arms. But that doesn't mean they're wrong. It just means they're hard to test. The effects are subtle, buried under layers of stronger forces, and often show up only at extremes we can't easily reach in experiments. Still, the math works. The models are self-consistent. And the beauty of it is undeniable, because it makes the universe feel more alive. Not a passive curved stage, but something dynamic spiraling, twisting, reacting to every spin and swirl of matter inside it. And maybe that's closer to the truth than we know. After all, nothing in the universe moves in a straight line. Everything rotates. Galaxies spin. Planets spin. Particles spin. Maybe space-time was never just bending. Maybe it was twisting the whole time, and we just didn't know how to look. If torsion turns out to be real, and it might, it would mean the universe isn't just shaped by what exists in it. It's shaped by how things move, how they twist, how they dance. And maybe, just maybe, the fabric of reality is not a flat sheet, or even a curved one, but a helix, spiraling into whatever comes next. Mirror matter. You ever get the feeling there's something right in front of you, something massive, something real. And yet, you can't touch it, can't see it, can't interact with it at all, like a shadow behind a wall. That's the idea behind mirror matter, a potential hidden twin of our universe, made of the same stuff but flipped, and the only reason we even suspect it might be there is because gravity refuses to let it stay quiet. Let's get straight to it. Physics is obsessed with symmetry. The universe seems to like balance, left and right, matter and antimatter, charge and spin. We build entire theories based on this stuff. But there's one symmetry that's always bugged scientists: parity. If you flip something like a mirror image, does it still obey the laws of physics? Turns out, not always. In the 1950s, scientists discovered that certain particles don't behave the same way when you reflect them. Parity was broken. That was a huge deal. It meant the universe wasn't perfectly symmetrical, at least not in the way we thought. But then came the question that still haunts particle physics. What if the universe restored that symmetry somewhere else? This is where mirror matter enters the picture. Imagine that for every particle in our universe, every electron, proton, neutron, there's a mirror version, same mass, same structure, same behavior, but flipped, not just like reflected light, but in their intrinsic properties, their handedness, their interactions. These mirror particles would form atoms, molecules, even mirror stars and mirror galaxies. An entire hidden universe. But here's the trick. It wouldn't interact with our matter in the usual ways. No electromagnetic force. No light bouncing. No chemical reactions. The only link between us and them would be gravity. Think about that for a second. A full-scale twin universe, occupying the same space as ours, but we can't see it, can't touch it, can't detect it with normal instruments. It passes through us like a ghost, but it has mass, and mass bends space. That's how we'd feel it, not directly, but through gravitational tugs and pulls that just don't line up with the matter we can account for. Now, if that sounds suspiciously like dark matter, you're onto something. Because one of the boldest proposals is that mirror matter could actually be what we've been calling dark matter this whole time. That invisible stuff holding galaxies together, keeping them from spinning apart. It might not be exotic at all. It might just be ordinary matter, but in the mirror world. And this theory does something that most dark matter candidates don't. It gives you a reason for the symmetry violations we see in particle physics. It says, sure, our world breaks parity, but the mirror world balances the scales. Together, the two halves make a symmetric whole. Now here's where it gets eerie. If mirror matter exists, it's not just floating out in deep space. It could be here, right now, filling the room around you, inside the earth, even passing through your body, and you'd never know because it doesn't interact. You could be sitting in a cloud of mirror atoms and feel nothing. No light, no heat, no collision, just gravity. And it gets crazier. Some versions of the theory suggest that mirror matter could form entire mirror planets, maybe even mirror life, a completely parallel civilization made of matter we can't see, living in a world we can't touch, right here in the same cosmic space. Not some alternate dimension, just a ghost layer of reality drifting alongside ours. So why haven't we proven this? Because detecting something that refuses to interact is absurdly hard. You can't shine a light on it. You can't trap it in a detector. The only hope is to catch the gravitational fingerprints. Anomalies in how galaxies rotate. Tiny imbalances in satellite trajectories. Maybe a weird pull in the early universe that we can only explain by something massive being there, but invisible. Some physicists have even proposed specialized experiments where mirror particles might occasionally interact with regular ones. Through rare processes or under specific conditions, but nothing conclusive yet. It's like chasing shadows in a world without light. Still, the theory refuses to die, because it's elegant. It explains too much. The parity problem, the nature of dark matter, the balance of forces, and maybe even why the universe feels like it's missing something, like we're only seeing half the picture. Maybe we are. So the next time you look up at the night sky and wonder what's out there, remember, the biggest mystery might not be what you can see. It might be what you can't. A whole mirrored universe, running alongside ours, shaped by the same rules, but hidden behind gravity's curtain. And if that doesn't make you question what reality even is, I don't know what will. Asymptotic freedom, you know what's crazy. The closer two things get in this universe, the more tension usually builds up. Stretch a rubber band, pull apart magnets, push atoms together. You feel the resistance, right? But quarks don't follow that logic. They flip it completely. Inside every proton and neutron are these tiny particles called quarks. They're like the smallest building blocks of matter that we know of. But here's where it gets weird. If you try to pull two quarks apart, the force between them gets stronger, not weaker, stronger. It's like the universe punishes you for even trying. You stretch them a little, and they cling harder. Stretch more, they grip tighter. And if you push them close together, they chill out. They act almost free. That's what physicists call asymptotic freedom. And it's one of those laws that makes you stare at the wall and question everything you thought you understood about how forces work. So let's break this down. The force that holds quarks together is called the strong force, and it is strong. The strongest force in nature by a long shot. It binds quarks inside protons and neutrons, and those protons and neutrons hold the nucleus of every atom together. Without it, matter would just fall apart. Reality would unravel. But unlike gravity or electromagnetism, the strong force doesn't fade with distance in a normal way. With gravity, for example, the farther apart two objects are, the weaker the attraction. Makes sense. Same thing with magnets or charges. But the strong force has this freak behavior. When quarks are crammed close together, like inside a proton, the force between them is almost nothing. They barely notice each other. It's like they're floating in a zero gravity zone. But start pulling them apart, even slightly, and the strong force flares up. It becomes more intense, like stretching a rubber band that never snaps. It just tightens and tightens until it snaps something else. Reality itself. You cannot isolate a quark. Ever. You try to pull one out of a proton, and eventually, the energy you put in becomes so massive, it doesn't stretch the bond. It just creates new quarks out of thin air. Yeah, the universe would rather spawn a whole new particle than let a single quark escape. That's how deep this thing goes. Now here's the catch. This whole idea, asymptotic freedom, wasn't even understood until the 1970s. It completely changed how we think about the strong force and won the Nobel Prize for the guys who figured it out. Because until then, physics couldn't explain why we never see free quarks. Why they're always locked inside other particles. It was one of those clues that the laws of nature are stranger and more brutal than we expected. And it's not just an odd rule in the background. It's a defining principle of quantum chromodynamics, or QCD, the theory that describes how quarks and gluons interact. Gluons are like the messengers of the strong force. They fly between quarks, carrying color charge, which is the weird version of electric charge in this world. But unlike photons, gluons also interact with each other. That's where the madness starts. Because the more gluons you've got bouncing around, the more chaos they stir up. And that chaos is what makes the strong force behave so aggressively when quarks drift apart. It's like being in a crowded bar fight. The farther away you try to run, the more attention you draw. You can't sneak out. The whole room turns on you. That's what it's like pulling a quark from its partner. Now, why does this matter? Because it shows you how deep confinement goes in our universe. Quarks are never alone. They live in permanent, high-stakes relationships. There's no freedom unless they're shoulder to shoulder. And the moment they try to get space, the universe clamps down. In a strange way, it's kind of poetic. The tiniest parts of matter, the roots of all things, are built on this unbreakable bond, an invisible leash that tightens with distance. No matter how much energy you pump into them, they can't break up. They just multiply into more particles that keep the cycle going. And here's the wildest part. This asymptotic freedom might have played a crucial role in the earliest moments of the universe. Right after the Big Bang, everything was so hot and dense, quarks were free, floating in a soup. But as the universe cooled, the strong force kicked in, locking them into protons and neutrons forever. That moment, when quarks became bound, was like the first real structure in the cosmos, the first bricks in the foundation of atoms, stars, planets, and us. So next time you look at something solid, remember what's holding it all together. Forces that don't act like anything we're used to. A world where closeness equals freedom and distance means destruction. Asymptotic freedom is more than just a physics term. It's a reminder that at the deepest level, the universe doesn't care if our logic makes sense. It has its own, and it's absolutely relentless. Superdeterminism. What if I told you that every decision you've ever made, what to eat, who to love, when to blink, was already baked into the fabric of the universe before you were even born? And I'm not talking about fate or destiny. I'm talking about physics. Quantum physics, no less. Welcome to the nightmare of superdeterminism. All right, so you've probably heard about the weirdness of quantum mechanics. Particles existing in multiple states at once, observing something changing the outcome. The randomness, the spooky action at a distance. But here's the part most people skip. All of that is based on one giant assumption, that we have free will. That when we measure a particle, we're freely choosing how to measure it, independent of the system itself. Now imagine if that assumption was wrong. Imagine if the very act of choosing what to observe wasn't really a choice at all. What if the particle, the measuring device, the observer, and even the so-called random number generator used in the experiment were all entangled in a giant cosmic script, written long before the experiment ever took place? That's superdeterminism. It says there's no true randomness, no true freedom. Every measurement outcome, every setting of your instrument, every thought in your head, predetermined, locked in. Like a movie you're watching frame by frame, thinking you're choosing where the plot goes, when really you're just along for the ride. Let's back up for a second. In the 60s, a physicist named John Bell came up with something called Bell's theorem. It's a way to test whether the universe is local and realistic, meaning information doesn't travel faster than light and particles have properties before you look at them. Spoiler alert, the tests failed. The results of countless quantum experiments suggest that reality is either non-local, meaning something here can instantly affect something over there, or the world just doesn't have definite properties until you observe them. That's when things got metaphysical. Some physicists accepted the randomness, others accepted the spooky connections, but a small, very uncomfortable idea stayed in the shadows. What if the entire setup was rigged? Because Bell's theorem assumes one crucial thing, that the settings on your detectors are chosen freely, randomly. But if they're not, if the universe is pre-written, all the way down to your fake coin tosses and random button pushes, then maybe those weird quantum results aren't so weird. Maybe they just look random because you were supposed to think they were. Now, that idea sounds gross. It feels like a conspiracy theory written into the code of reality. Because if superdeterminism is true, then the whole concept of doing experiments to learn about the universe breaks down. It would mean the universe is not only deterministic, it's deterministically hiding the fact that it's deterministic. Like it's gaslighting us with probability. The implications go further than physics. They hit you in the gut. If your choices are just part of the script, then what exactly is making the choices? Your brain, also pre-written. Your environment, pre-written. Your reactions to this video, all coded into the laws of nature from the beginning of time. Free will becomes an illusion, a side effect of a system that makes you think you're steering when you're just along for the ride. But here's the uncomfortable twist. There are serious physicists who are exploring this idea right now. They're not cranks. They're researchers trying to resolve the paradoxes that quantum theory keeps throwing at us. Because the current interpretation, that particles have no properties until you look, is weird too. Unreasonably weird. And some would rather believe in a cold, absolute determinism than an untamed, observer, dependent universe. Now, to be fair, superdeterminism is incredibly hard to test. Because if you design an experiment to test it, well, the theory just says your decision to test it was also predetermined. It closes every door before you even knock. It's like the perfect escape artist. You can't trick it because it says every trick you try was always part of the act. Still, some researchers think we might find cracks in the idea. Maybe by looking at correlations so deep and subtle that they reveal a hidden pattern. Maybe by building systems that can't possibly be predetermined. If that's even a thing. But nothing has done it yet. Right now, superdeterminism just sits in the corner of physics, arms folded, waiting. And that's what makes it so terrifying. Because if it turns out to be true, it doesn't just change physics. It changes how we understand ourselves. It flips philosophy, ethics, choice, creativity, everything, on its head. It turns the universe into a fully automated storybook, where even rebellion was just another chapter. So next time you think you're making a spontaneous decision, consider this. What if you were supposed to think that? What if the choice was always an echo, not a spark? What if freedom is just a side effect of not seeing the whole picture? And if that doesn't melt your brain, nothing will. Spontaneous symmetry breaking in the Higgs field. There was a moment, just after the Big Bang, when everything in the universe was perfectly balanced. No mass, no weight, no friction. Just pure energy, moving at the speed of light. Particles didn't really exist the way we think of them now. It was all motion, all symmetry, all uniform. And then, something snapped. Something broke that perfect symmetry. And because of that one tiny glitch in the early universe, things suddenly started having mass. Not because someone flipped a switch, but because a field, invisible and everywhere, froze in a weird direction. That field is called the Higgs field, and what happened to it is known as spontaneous symmetry breaking. Now hold up. What does that even mean? All right, picture this. You're standing at the top of a perfectly round hill, and you're balanced right at the center. Every direction looks the same. That's symmetry. Nothing about the landscape tells you where to fall. But the moment you lean, even just slightly, gravity takes over and boom, you roll in one direction. Suddenly, the symmetry is broken. Not because someone pushed you, but because the balance was so perfect it couldn't last. That's basically what happened to the Higgs field. In the earliest moments of the universe, the Higgs field was symmetrical, totally flat. Particles passed through it with no resistance. But then the universe cooled just enough, and the field dropped into a lower energy state. But instead of settling evenly, it picked a random direction in this invisible energy space. A direction that gave certain particles resistance, and that resistance is what we now call mass. Let me say that again. Mass is not something particles just have. It's something they get by interacting with the Higgs field. The more they interact with it, the heavier they become. Some particles barely touch it, like photons, and they stay massless. Others wade through it like syrup, dragging as they go. That's what gives us things like electrons and quarks, and eventually atoms and stars and everything we touch. It's wild. The entire physical structure of the universe, from your bones to black holes, depends on this field picking a random direction and breaking a perfect symmetry that once ruled everything. Now here's where your brain starts to warp. This wasn't caused by anything. No event triggered it. No outside force. It just happened. The symmetry was so delicate, so balanced, that it was unstable. And that instability is what caused the field to fall out of symmetry, spontaneously. Like a pencil standing on its point, it doesn't take a gust of wind to make it fall. The balance itself is so impossible that the fall is inevitable. And once the Higgs field broke symmetry, it stayed broken. The universe locked into a new state of being. From that point on, particles moved through a field that pushed back. That drag, that resistance, is what we experience as mass. This concept is baked into the standard model of particle physics. Without it, the whole theory collapses. The equations literally do not work unless particles get their mass from a field like this. That's why the discovery of the Higgs boson in 2012 was such a big deal. It was the ripple in the field that proved the field itself exists. It was like finding a drop of water in the middle of the desert and confirming there's an entire ocean under the ground. But the part that still bakes everyone's brain is that word, spontaneous, because it means the universe chose a path, not based on logic or laws, but on a kind of cosmic randomness. It's like building a perfectly symmetrical temple, and then a single stone decides to tilt, and everything that happens after is based on that tilt. Space, chemistry, life, all because the Higgs field shrugged in one direction instead of another. And the real kicker, it could have tilted the other way. In another universe, maybe it did. Maybe particles there are heavier or lighter. Maybe atoms never formed. Maybe symmetry breaking in that reality led to something totally alien. In fact, many physicists believe that spontaneous symmetry breaking could be the reason we have this particular universe at all. And that there could be countless other ones where it broke in different ways, creating entirely different laws of physics. So yeah, mass, the thing that lets stars burn and feet stay planted on the floor, might not be some fundamental feature of matter. It might just be a side effect, a cosmic accident, the result of a perfect symmetry that could not hold, and the weirdest part is it had to happen. Because perfect symmetry is beautiful, but it's also empty. It gives you no structure, no diversity, no texture. The moment it breaks, reality gets interesting. Structure emerges. Complexity begins. Without it, the universe would still be a featureless soup of light and energy. So every time you feel the weight of something, a book, a body, a planet, you're feeling the echo of that ancient symmetry breaking. You're feeling the Higgs field pushing back, ever so slightly, on the motion of particles that used to fly free. And that, somehow, is what lets the universe build anything at all. Bubble universes. Imagine the entire universe. Everything you've ever known, stars, galaxies, time itself, just a single bubble, floating. And surrounding that bubble, nothing you can touch, but maybe an infinite foam of other universes, each sealed off, each living by its own bizarre set of rules. Ours is just one. That's not science fiction. That's one of the most mind-twisting ideas in theoretical physics. It's called eternal inflation. And the result of it is something called bubble universes. Here's how it starts. In the earliest moment after the Big Bang, and we're talking fractions of a fraction of a second, space itself didn't just expand. It exploded. Rapidly, faster than light. This period is called inflation, and it's not just a theory. It explains why the universe is so flat, so uniform, even though light didn't have enough time to smooth everything out. Inflation is what took the chaotic fireball and stretched it into something cosmic and smooth. But the real kicker is that inflation may have never truly stopped. In some regions it ended, and when it did, a bubble universe like ours popped into existence. But in other regions, and is still going, space is still stretching endlessly, forming more and more bubbles, forever. Now, inside each of these bubbles, the laws of physics might be different. That's the part that really breaks your brain. One bubble might have stronger gravity. Another might have no electromagnetism. Maybe some have no particles at all, or no time, or no concept of energy as we understand it. Some might be complete chaos. Others, maybe, give rise to something like stars and life. But here's the thing. These bubbles are sealed off from each other. They can't collide. They don't mix. Each one is its own private reality, and we're inside one of them. You might be thinking, all right, that sounds wild, but how could anyone possibly know this? That's the creepy part. The math suggests it. Inflation works too well. The theory predicts more space than just what we see. And because quantum fields behave probabilistically, different patches of space fall out of inflation at different times, creating bubbles in an ever-expanding sea of inflating space. So just like boiling water creates bubbles of steam, the quantum vacuum, that invisible backdrop of reality, can spawn entire universes. And what's even weirder, these bubble universes aren't in our space. They are their own space. They do not float in our universe. Each bubble comes with its own space and time, so there's no traveling between them. No telescope can ever see past the walls. If you were born inside one, it would feel like the only universe that ever existed, which, for us, it does. Now let this hit you. This idea, eternal inflation and the bubble multiverse, might not just explain why our universe exists, it might explain why it looks fine-tuned. Why things like the charge of an electron or the strength of the strong force seem perfectly dialed to allow stars, planets, chemistry, even life. Because if enough bubbles are being formed, then somewhere, by pure statistical accident, one of them is going to have just the right conditions. That one turns out to be ours. This is what's called the anthropic principle. You're here, asking why the universe seems perfect only because it had to be, or you wouldn't be here to ask. Out of the infinite bubbles, most are probably sterile, dead, but you ended up in one where everything aligned. It feels miraculous, but in the multiverse view, it was inevitable. Somewhere, sometime, someone was going to get lucky. Still, none of this is proven. And that's the haunting part. You can't test for other bubbles. They are too far, too separate. The edge of our universe is an impenetrable wall of light. No information gets through. So as far as you're concerned, the rest might as well not exist. But you can't unsee the math. You can't ignore that inflation, when you run it through the equations, doesn't stop neatly. It naturally creates more space, more bubbles, more universes than anyone ever asked for. The theory didn't start with the idea of a multiverse. That part fell out as a side effect. And those are always the ideas that sting the most. The ones nobody went looking for, but couldn't deny. So maybe we live in just one isolated patch of a far stranger reality, a single soap bubble in an infinite quantum foam. Maybe our Big Bang wasn't the beginning, just a beginning, one of countless others. And maybe, right now as you listen, new bubbles are forming. New universes are being born, each one with a completely different fate. No way in, no way out. Just infinite beginnings, sealed in their own time, forever out of reach. And we're left here, floating in our own, wondering how many others are out there, wondering if we'll ever know. But maybe, just maybe, we were never supposed to. Dark flow. All right, this one is going to make your brain feel like it's sliding off the edge of a table. Imagine you're floating in space. Not just above Earth, not just outside the galaxy, but so far out that you can see entire clusters of galaxies. Thousands of them, stretching across the sky. Now imagine that some of those clusters are all moving in the same strange direction. Not randomly, not because of gravity from anything nearby, but because they're being pulled hard in one direction by something we cannot see, by something that might not even be inside our universe. That's the mystery of dark flow. When scientists looked at how galaxies move through space, they expected some randomness. After all, gravity from different structures should tug on them in various directions. But when they mapped out this movement using data from the cosmic microwave background, that afterglow of the Big Bang, they noticed something bizarre. Huge swaths of the universe, covering billions of light years, were all drifting the same way. And they were not just drifting, they were speeding, hundreds of kilometers per second, toward a specific part of the sky. But here's the catch, there is nothing there. No massive cluster of galaxies. No supervoid. No dense patch of dark matter that could explain the pull. It is as if something outside the visible universe is tugging on our entire cosmic neighborhood. That should not be possible. According to standard cosmology, the universe beyond our observable horizon should not be able to affect us. It is too far. Light from those regions has not had time to reach us since the Big Bang. They should be causally disconnected. In other words, no influence, no effect, no pull. But dark flow flips that assumption on its head. It suggests that something beyond our cosmic bubble is reaching in, grabbing massive chunks of space, and pulling them its way. Now, let's be clear. This is not some fringe fantasy. The original observations came from NASA's Wilkinson Microwave Anisotropy Probe, WMAP, and later data from the Planck satellite has challenged some of the findings. But the idea still lingers, because even if the data is messy, the possibility it raises is enormous. If dark flow is real, then we are brushing up against the edges of something much bigger than we ever imagined. Here's one of the freakiest possibilities: the multiverse. Yeah, that old idea again. But this time, it is not just speculation. If other universes exist, and if they are physically real in some broader landscape of reality, then they might bump into ours. Or worse, they might pull on it. Not with gravity the way we know it, but with some deeper interaction we do not yet understand. Dark flow could be the fingerprint of another universe bleeding into ours. Think about that. A kind of cosmic undertow, where the gravity of a neighboring universe is dragging parts of ours toward it. But there is another possibility. Maybe it is not another universe. Maybe it is a leftover structure from before the Big Bang. Yeah, before. Some theories suggest that the Big Bang was not the beginning, but a transition, a bounce, or a collision of higher, dimensional objects in string theory. If that is true, then relics from that pre-Big Bang era might still exist, outside the edge of our visible cosmos, and they might be bending space in ways we cannot see. Dark flow would be the ghostly pull of that hidden architecture. Whatever it is big. We are talking about motions of hundreds of millions of galaxies. That is not local turbulence. That is something rewriting what we think space even is. And here's where it gets even crazier. If this flow continues, and we cannot see the edge of it, then we might actually be falling into something. Over cosmic timescales, our entire observable universe might be drifting toward an invisible mass, a great attractor beyond the edge of reality as we know it. But we will never reach it, because the expansion of space is also accelerating. Dark energy is pushing galaxies apart faster than gravity can pull them together. So while dark flow might tug on our universe now, eventually everything will be moving away from everything else so fast that even this mysterious pull will be drowned out. Galaxies will vanish from view. The flow will slow, and we may never know what was behind it. That is what makes dark flow so disturbing. It is not just about movement. It is about the edge of knowledge, the idea that there are forces at work, right now, that we will never be able to trace back to a source, that somewhere beyond our reach, something massive, or ancient, or alien, is shaping the way our entire universe moves, and we only noticed it because of a subtle tilt in the microwave radiation leftover from the Big Bang. So the next time you look at a night sky and think about stars drifting quietly in space, remember this. They are not just drifting, they are being dragged by something we may never see, something outside the map, outside the story, maybe even outside existence as we understand it. And that pull is still happening. Chameleon Particles. Okay, this one is going to sound like science made a deal with magic. Imagine a particle that hides in plain sight, not just by being small or fast or quiet. No, it literally changes what it is depending on where it is. It adapts to its environment. It shifts its properties like a chameleon changes color. That's not a metaphor. That's what these things are actually called, chameleon particles. And if they exist, they could be one of the biggest missing pieces in modern physics. So here's the weird setup. For a long time, scientists have been trying to figure out what dark energy is. That mysterious force that's making the universe expand faster and faster. Not just expanding, accelerating. It's like the universe is pressing the gas pedal harder over time, and nobody knows what foot is on the pedal. And that's where chameleon particles come in. The idea is this: what if the reason we can't detect dark energy directly is because it's hiding behind something that morphs its behavior depending on its surroundings? Like when you're deep in empty space, say, between galaxies where there's barely any matter, this particle is light and free and able to stretch space apart like a cosmic balloon. But the moment it gets near regular matter, like Earth or atoms or lab equipment, it bulks up, gets heavy, becomes sluggish, and suddenly it doesn't interact the same way. Basically, it becomes undetectable. This is why it's called a chameleon. Not just because it changes color, but because it adapts to pressure. In high-density environments, like on Earth, the chameleon field becomes short-ranged and heavy. But in low-density space, it becomes light and long-range. It stretches across the cosmos without us seeing a thing. This shifting quality is what makes it such a brilliant and frustrating candidate for dark energy. If it's real, it explains why dark energy is everywhere and yet invisible to us. Every time we try to trap it in a detector or observe it in a lab, it transforms. It blends in. It becomes something else. You can't study a ghost that changes form the moment you shine a light on it. And this isn't just theory for theory's sake. There have actually been experiments, real ones, designed to test for chameleon fields. One involved bouncing a laser beam between two mirrors in a vacuum chamber. The idea was, if chameleon particles exist, they might get trapped between the mirrors, causing a tiny delay in the light's path. Not enough to notice with your eyes, but enough that ultra-sensitive instruments could pick up the hint of a presence. Results so far: no smoking gun, but also no complete shutdown of the idea either. That's the part that keeps physicists up at night. The chameleon theory is slippery. It's designed to evade detection in dense environments like ours. So every null result could still be consistent with it, which means we have to keep chasing shadows until one of them finally casts something real. But it's not just about dark energy. Chameleon particles mess with the very idea of what a particle is. Normally, a particle has a mass, a charge, a spin, fixed properties. But chameleons break that rule. Their mass changes depending on where they are. That's like throwing a baseball on Earth and having it behave differently in space. Not just because of gravity, but because the baseball itself changes weight. This violates our expectations on a deep level. It suggests that the universe isn't just a set of rules. It's a negotiation. Particles aren't just playing a role. They're adapting to the stage. And if the chameleon field is real, it might be connected to other mysteries too. It could help explain why gravity is so much weaker than the other forces. It might interact with photons, the particles of light, in a way that causes slight distortions in high-energy beams traveling through the cosmos. These are all open questions, waiting for the right test, the right observation, the right flicker in the data. But let's be honest, the real reason this idea is so captivating isn't just the physics. It's the vibe, it's the image. The thought that the universe is full of shifting forces. That empty space is not empty. That particles might be lurking all around us, wearing disguises. And that the reason we haven't found the answers is not because we're looking in the wrong place, but because reality itself is hiding. We tend to think of physics as hard, fixed, cold truth. But chameleon particles say otherwise. They say nature plays tricks. It adapts. It conceals. And if we want to uncover the deepest laws of the cosmos, we can't just ask louder. We have to get smarter. Because what we're chasing might be changing right in front of us,